Jim, should we check if all the jurors are here?
Let's check. One,
Neil
two,
is
three,
here.
four, five, six,
Oh,
eight,
okay. Good to
nine.
see you again,
We have
Neil.
nine jurors that, oh, never mind. We have 10. One, two, three, four, five, six, seven, eight, nine. Oh, actually, just nine.
Yes,
See
good to
who
see you
are.
again, Jeffrey.
Yep. And science too fun, I would say.
Are you fourth year now?
First third year.
Okay. What option did you pick?
And fifth.
Okay, very good.
Yeah. Louis is in ensign, by the way.
I was just
Yeah.
talking with Neil a second ago. Yeah,
Yes. You're in first year, Louis?
yeah, first year. Although I'm also going to Antfizz, the typical option.
You want to go to physics. Okay.
Yeah.
We have a lot of entrance people next year. This year we only got 10 entries, by the way.
It's
Are
always
there
been
more
the smallest
aerospace?
option.
So,
Exactly. Other
so
than
have
Except
all
that
the
time when,
team...
before your time, there was nano engineering that always only had 2 or 3 people.
Of course they cancel it.
Nano engineering sounds like me.
Oh no, Jim.
But yeah. Okay, so who is missing from our juror team?
Uh,
Let's call everyone's name and they could answer if they're here or not.
Louis, your
So
accent changed as well.
he's Singaporean or whatever accents
Oh
right now, I
yeah,
can
after
tell.
coming back from CaYPT, I guess I've become Singaporean.
No, you become more and more Singaporean right now, though. Like
GG.
yesterday I met you
so
on campus. I was like, well, who the hell are you? Why are you speaking like that?
Wait, did you meet
okay.
I guess
Let's
the
let's
top
do a
member?
juror check. Let's do a juror
Let's
check.
do George check
So
first.
Alessandro is
Oh, first
here,
name,
I
last name.
believe.
Okay, sorry. I have to be
Matt
more
is
professional.
here. Gorav is here, right? Yes. Neil is here. Uh, is okay. Devyash is here. Uh, Atkarsh is here. Mohammed.
Muhammad is here.
Okay. And then Hinab,
Here too.
is he here? Okay, also here. Uh, Tanya.
Yep, I'm here.
Tanya is also here. And then
Tanya is here.
Atkarsh. Is Atkarsh here?
Akash is here as well.
Okay, then we have everyone then.
We
Okay.
have everyone.
How
Fantastic.
about the teams? Do we have let's see who Shroomskis, are you guys here?
Yes, we are here.
Okay, perfect. And operation
Ahorn syrup.
yes, Ahorn syrup, yes.
Yes, we are complete.
And then we also have Team Excel. Are you guys here?
Yeah.
Okay, then we are ready to start then. Then I guess we'll pass it to Luyu and Z. We'll run the clock and run the fight. Good luck, everyone. Hope you enjoy the finals.
And by the way, for the teams here, the participant, you guys must turn on your camera for the finals. And should we have a quick introduction of themselves? Yeah, maybe. Let's have a quick introduction for yourself. Maybe we'll start by the teams and then to the jurors. And let Shroomski start first, following the order.
Okay, hi there. We're Team Shroomskis. We're from UTS. We're mainly grade 12s, and we hope to have a great match. And Germany, please be nice to us.
Okay. All right, now for team Operation Ahorn Syrup.
Hi, I'm Alan. I'm from Germany. We are competing from various parts of Germany. Well, we hope to have an interesting discussion. We're mostly 12th and 13th year. But yes, you should be scared of us. We will try our best to destroy your physics projects. I'm just kidding, of course. Good luck.
German invasion. Okay, now Team XL.
Yeah, so I'm Luke. I'm from Team Excel. We're a private team. Germany and Shroomskis, please be nice to us. I know we're in a very late third place, so I'm happy we're here already. That's the only thing that matters.
Not ambitious, eh? Okay, now let's go to the juror. Maybe we'll follow the order on the Zoom participants. Maybe like Abhinab.
Hello all, I'm a PhD student in particle physics.
working at Sun. I'm excited to be a juror.
All right, thank you. And now we have Akash.
Hello, I'm a third year PhD student in geophysics at the University of Alberta, and I work on seismic reconstruction for carbon capture projects. And this is my second year juroring at CaYPT, and I'm back again this year for the memes.
For the memes. All right. So next, let's have Alessandro.
Hello everyone, I'm Alessandro. I'm a PhD candidate at the University of Toronto. My research concerns open quantum systems, so theoretical physics applied basically to quantum systems that you really find in nature. And I'm very glad that this is my third year that I participate as a juror in this wonderful competition. Very glad to be there, and thank you very much to organizers, and very good luck to all the teams. I mean, it's a lot to stay in final. Thank you.
Thank you, Alessandro. And now let's have Divyash.
Hello there. I'm Divyesh, master's student in condensed matter theory, and I'm excited to be a juror today. Thank you.
Thank you, Divyash. And now let's have next be Agorav.
Hello everyone. I'm a second year PhD student at UFA. I work in astronomy and astrophysics. Basically, I look at stars all the time.
Oh, all right. Thank you. And now next, let's have oops, sorry. I think I closed the list just now. Let's have Matt Ford.
Sure. So I'm a graduate student in the West Coast, Canada. My primary research interests are random matrix theory and quantum chaos. So I mostly do just theory. Yeah. Good luck, guys.
Fantastic. And let's have Mohammed. Mohammed Osama.
Sorry about that. Hope
Oh,
you can hear me.
no worries. Yes, I can hear you.
All right, yeah. So I recently graduated with a PhD from the University of Toronto. I focused on infrared spectroscopy, so I was building stuff in the lab, and I also measured some greenhouse gases. So basically experimentalist. And throughout the tournament, I saw some very impressive work. So very impressed. When I was at high school, I was not at that level. So you guys are at a very good position, and good luck with the finals.
Thank you, Mohammed. And let's have Neil.
Hello, everyone. I'm Neil. I did my undergrad and master's in University of Toronto, engineering science, and then UTIUS. And now I'm working for Department of Defense in Ottawa. I'm in the space systems group working with satellites because I did aero option. And this is my 8th or 9th year. I forget which.
Oh.
Yeah. I think I predate Jim. So
Yes. This
Yeah.
year is our 10th anniversary of CaYPT. Yes.
Yeah, Neil was here way before when I had know what CaYPT is. So, all right. So next, let's have Tanya.
Hi everyone, I'm Tonya. I did my undergrad in medical physics at McMaster University, and I did lots of research in liver cancer, and now I'm doing radiation therapy at U of T, and I'm in my last year. Good luck, everyone.
Thank you, Tanya. All right, fantastic. So now the presentation is gonna be as such. So first of all, it will be Team Excel presenting problem seeing ruler, and then next will be Team Germany presenting ring fountain, and the last will be Shroomsky presenting magnetic Newton cradles. So for Team Excel, I believe Germany will oppose Team Excel, and then Shroomsky will be the reviewer first. And then for the next round, when Team Germany is presenting, Shroomsky will oppose Team Germany, and Team Excel will be the reviewer. And for the last round, when Team Shroomsky is presenting Cradle, I believe, oh, sorry, I think Team Excel would oppose Team Shroomsky's, and Team Germany will be the reviewer at this point. So following this order, the first round will be between Team Excel being the reporter, Team Germany being the opponent, and Team Shroomsky being in and Team Germany, sorry, Team Shrunsky being the reviewer. So let's do this.
Let's check with the teams to make sure that this is what they expect. Is this what you expect, or like are we doing this correctly?
For all the questions proposal, just double checking.
Yeah. Louis, feel free to speak up if there are any problems.
I think I'm pretty sure it's correct. Like, let's double
Yeah,
check.
the problem selection should be fine. I'm just
yeah.
Double check
the
with Jeffrey.
order?
This seems fine, and then we'll lock this in.
Oh yeah, the order is correct because Shrunsky is the last
Yeah,
to present.
the order is correct. But do you believe that Germany should be opposing Shroomski's, or
Germany is
Excel?
not opposing Shroomski. I think Excel is opposing Shroomski.
Let's lock this in then. Sure.
Yes. Okay, yes.
Sounds good.
Okay. So then we'll start immediately then, without further ado, I guess. So Team Excel, Z, do you want to start the clock? Team Excel will be presenting Singing Ruler, and they will have 3 minutes to prepare their presentation.
You can see the clock in Z's like camera, OBS. So enjoy and you're ready.
Sorry, the timer now is for 1 minute.
The reviewer presentation, this follows the CaYPT format. Oh, no, sorry. 1 second. Z, you probably need to move forward because this is for problem selection. Click another time? Yes, now we're on. All right. Thanks for pointing it out.
Sorry, maybe I missed something because I don't see the timer.
Oh, the timer is in Z Qin Pong's camera, OBS.
Oh,
It's
yes,
not shared.
let's see, yes.
Okay.
Yeah, can I start if I can? Oh, wait, how does he turn down?
Yeah, Louis, you take the
Sure.
lead.
So Z, can you please move on to the next phase, and then we'll start when Ray is ready. So Ray, you'll have 12 minutes to present problem D, the singing ruler, and you can begin
Wait,
now.
yeah.
Or-
Wait, sorry. Can you
Yeah.
see? Wait, can you check if you can see my? Sorry, give me a second.
Yes.
Okay. Yeah.
Your screen share is visible. Yes.
Okay. Yeah. I guess I'll start then. So yeah, hello. My name is Ray. I'm on Team Excel, and today I'll be reporting for problem D, the singing ruler. The problem statement reads: when a ruler is clamped at one end and struck, it oscillates and emits a characteristic sound. Investigate how the sound depends on relevant parameters. So the parameter that we identified was the length of the ruler, the Young's modulus, the mass of the ruler, and the distance from the source. So here's an overview of the presentation, and I'll be starting with the introduction for the problem. So here's a video clip of the ruler vibrating. And when the ruler is vibrating, the sound is obviously coming from the ruler and it's causing it to vibrate up and down, causing it to be disturbed. However, one thing that we noticed in our preliminary observation was that the table will also sometimes vibrate with the ruler. And due to the bigger surface area vibrating, it will actually emit a lot more power compared to that of the ruler. This is confirmed by testing what the sound will be like when the table is damped when we place a piece of cloth over it. The sound heard when this was done was a high frequency, low amplitude sound wave, was somewhat quieter than with a table. Obviously, we tested this with different tables, and the size of the platform and the shape of the platform all contributed in different ways, with some shapes amplifying the sound significantly, just like how a sound is amplified in a resonance box. Because of the complexity in characterizing the shape and the size of the table, the vibration of only the ruler is considered. So for the quantitative explanation for the sound, as you move away from the source, the sound you'll be hearing is based on the pressure at that point. And this can be characterized by using 3 different equations, which are the acoustic power, the sound intensity, and the formula to actually translate it to a format that we can understand easily, being the decibel scale. The acoustic power is just the integration of pressure squared over the air density times velocity of sound in air, or it can be written as the sum of the different vibration modes, with A being the amplitude of each mode. The sound intensity as a function of the distance r over the sound from the sound is just the power divided by the surface area of the propagation, being 4 pi r squared. As the area of propagation increases, the power is conserved, but the intensity decreases. Lastly, the decibel, where the soundness based on the loudness, is being based on a log-based formula, being 20 times log 10 of PRMS divided by the base pressure. So now we'll be going into our experimental setup. So here's the overall setup, which includes a clamp that will hold a ruler to the table with 2 platforms that will serve as a phone stand in the background. The phone will record and the background will distinguish the ruler to make it more clear. If sound recordings are needed, a microphone will be placed next to the ruler instead. The distance between the ruler and the microphone can be adjusted so that the acoustic intensity based on distance can be accurately tested. So here's what the setup looks like in real life with all the different components, and the microphone that we use being the Memo app, and the sounds analyzed using an app called Audacity, and the motion of the ruler is tracked using the tracker. And here's just another view of it. So yeah, you can see we use the red piece of tape to differentiate the end. So the Young's modulus and the second moment of area are crucial parts of this problem, measuring an area's resistance of deformation and resistance of bending in the cross-sectional area respectively. They can both be found by using these formulas with these respective variables. Experimentally, it can be found by attaching a mass to the hanging end and seeing how the time for a cycle changes for different masses. The bigger the change in the period for a given mass, the smaller the E value and vice versa. Plotting the t versus the time squared, the E can be found by using the fit line. Using this, we obtain the E for the plastic ruler to be 1.8 times 10 to the power of 9, and the E for the metal ruler to be 4 times 10 to the power of 10. So in our theoretical model, we'll be starting with the Euler-Bernoulli beam theory, So some assumptions include an ideal vibration condition with constant vibrations that doesn't include losses. Secondly, we assume that the beam is slender, so the deformation normal to the length can be neglected. We can also assume that the beam has an even distribution of material throughout the length from the mass, density, volume, and whatnot. So the governing Euler-Bernoulli beam equations M, which are the forces parallel to the cross-sectional area, is equal to EI multiplied by the double derivative of the transverse displacement function, with W being the transverse displacement, X being the distance from the clamped end, M being the bending moment, E being the Young's modulus, and I being the moment of area. So this can be rewritten as an expression for shear force, which are the rotational effects caused by the bending of the ruler perpendicular to the shape of the ruler. For clarifying purposes, nonlinear beam theories such as von Karman or Rayleigh beam theories could be used, but for displacement of some small magnitudes, like in our experiment, we thought it was unnecessary. However, there's still an overarching problem, and that's the fact that the displacement function Wxt is not solved. So this is done through a small section of the beam, and the forces acting through the smallest element will give between X and X plus delta X will give the net forces acting on it. The beam experiences internal shear due to bending, and because of the spatial variations, the shear on both sides are different. The resulting net force must be equal to the mass of the element multiplied by its transverse acceleration. And by expanding the expression, the equation can be written entirely in terms of its transverse displacement. So splitting the transference into the time and space function, each of them can be solved individually. And this can be used to find the frequency and amplitude, with the frequency assuming an initial impulse is given. And the frequency of the ruler will be the frequency it makes, and the amplitude is directly related to the sound pressure and the amplitude, which we'll talk about in part B and part C. Given the input parameters and the shape of the equation, we can accurately determine the shape of the ruler, since it only depends on the vibration mode. The harder you flick it, the more it will excite the higher modes. But for this problem, we will only be considering the first mode, since the vibrations used in the experiments are not strong enough to excite the other modes. Part of the time function is still not solved yet, since the damping is not accounted for. So firstly, we assume that the ruler's frequency doesn't decrease, only the amplitude does. Next, the fixed end is perfectly rigid, meaning no energy is lost to the clamp. This assumption simplifies the formula so only the damping forces due to air resistance and internal friction will be considered. Lastly, we assume that the gravity doesn't affect the damping since the object is too light. We can take a look at the geometry of the setup first. And for a decaying vibrating ruler, it will vibrate with a smaller and smaller amplitude. And these variables will be defined with t as a function of t being the position based on time, a being the initial amplitude, and e to the power of negative zeta times frequency times time is the exponential decay with the decay, and with zeta being the decay ratio or damping ratio. The two frequencies are the natural and damped frequency, and phi is the phase angle. For this problem, the use of a damping ratio is implemented, as losses are hard to characterize by themselves, so they're just grouped together for simplicity. So for a general underdamped system, the Garmin equation is this, and this can be applied to two different cases, one where the ruler has its starting displacement or an applied impulse. The initial displacement can be modeled as a cosine, and the impulse can be modeled as a sine. In real life, it's likely a mix of both cases of displacement and impulse, since a strike cannot be modeled perfectly. For this problem, we decided to do experiments based on a starting displacement model due to its simplicity. However, they are quite similar and only depend on different constants or parameters and differ by pi divided by 2. Experimentally, we found that the period of oscillation through the standard formula 2 pi divided by WD, and this can be applied to multiple cycles nt. Next, the time can be applied to the exponential decay term to solve for the decay. And logarithmic decrement delta can be found by using the difference between the amplitude found by the time-based displacement formula when cosine equals 1, and ax being the x peak and m being the gap in between the two peaks used. By taking the natural log between the two peaks, the logarithmic decrement formula is found. This can then be applied and rearranged into the formula for zeta. From the experiments we did, we can see excellent experimental and theoretical fit. Now we have solved for the full range of the motion of the ruler, which will provide the amplitude of the waves that are propagating in frequency. The errors of the frequency here can be attributed to the fact that the theoretical frequency is not considering the loss, and the fact that the frequency also decays slightly, but it should be minimal. For our last theory, we investigated the sound production and how it actually transfers to acoustic pressure. So for assumptions, we can assume that the ruler has no deformations. We can also assume that the vibrations are small, since larger vibrations has more modes that will be hard to separate. And these harder modes will also decay faster, so even with fast Fourier transform, they will be hard to detect. Lastly, we can assume that there will be no fluid effects of the air and assume that the sound is a perfect wave. Starting from the acoustic power, it is defined as the radiating efficiency times air density times the speed of sound multiplied by the integration of the VRMS squared to the surface area. The only part of the formula that's unsolved is the velocity, which can be solved by using the standard VRMS formula. As the wavefront increases, the power is conserved due to energy conservation, but the intensity is decreased, as the intensity is inversely proportional to the propagated area, which will explain the decrease in the acoustic amplitude. However, we still haven't found the VRMS, and it's defined as the square root of 1 over t times the integration of function of v given the time and position. Simplifying this by using the derivative of the space equation found in part 1, w as a function of x and t, the VRMS can be simplified by integrating the sine squared and the velocity squared under the square root. The final VRMS is then obtained being the angular velocity times a times the normalized shape mode amplitude divided by the square root of 2. So acoustic intensity can be defined acoustic intensity can be defined using by the square of the PRMS over the air density and airspeed, and power is defined as the surface of propagation times intensity. By using these two formulas, the final PRMS, or the pressure, can be found by obtaining it as a function of radius through rearrangements. The final parts of the parts in the final pressure formula are either all constants or easily found, such as the air density, pi, and airspeed, or is found through analysis of velocity and other aspects of sound. From the integrations, we did all of our calculations in decimals and sheets. So the sound can be plotted by using the decibel transformation formula, and as you can see, it follows a clear logarithmic trend. And plotting the sound amplitude versus the Now we'll be moving on to the key parameters. We have found that the length and the mass of the ruler all have negative correlation with the frequency, and Young's modulus has a positive correlation. For the acoustic pressure and amplitude, the distance from the source has a negative correlation. These two factors, frequency and acoustic pressure or amplitude, essentially make up a sound. So with the length, we can see a nonlinear downward trend for both the plastic and the metal ruler, and which is a similar case for the mass. And the Young's modulus is a positive effect on the frequency of vibration, as is a trend that's similar to a square root function. And we could not test for the E value or the mass, since we had to ensure that all of the variables are the same, which is hard to find a ruler exactly with those dimensions. Lastly, you can see that since the sound uses a log scale, the distance from the source doesn't affect the amplitude of the sound significantly. Eventually, the sound amplitude should asymptote or decrease very slightly. So in conclusion, we had an experimental setup that could test the physical vibration of the ruler and the sound, and also characterize the Young's modulus and the second moment of area through experiments. We consider the relevant parameters in a detailed model of the sound and the transverse displacement of the ruler, varying key parameters and the amplitude of frequency. And overall, I think we had a good understanding of the problem, including the sound production elements, sound frequency, sound amplitude, and the decay over time and space. Here are references, and thank you for listening.
Sure. Great job. Let's now move on to the rapid fire from the opponent to the reporter. You'll have 2 minutes, starting now.
Awesome, thanks. So starting off, you showed us your experimental setup. I just want to ask, by clamped, how did you clamp it and where exactly did you clamp it?
Oh, we clamped it by just using like a conventional clamp, and we varied the length.
Did you change where you clamped it relative to the table and the edge?
No, we clamped it to the edge.
And how do you define the characteristic sound?
Characteristic sound, propagate speed, and yeah, it would just look like a wave.
All right.
Yeah,
did you look at the initial displacement of the ruler while you're striking it?
Initial displacement, we did not investigate it because we just displaced it, and that will obviously just be the starting amplitude. So we did not see a lot of point in investigating how it would change, because the starting displacement will obviously just be how much we displace.
Okay, I asked this because in all your graphs, I don't see errors. So I wanted to ask, how many times did you iterate for a same set of parameters? And if you were able to keep the amplitude and everything consistent.
Yeah, we displaced I remember it was 5 centimeters from the equilibrium position, and we were able to keep most of it. Sorry, I'll get to your error bar. And so for the error bars, we tested each of them.
Yeah, how exactly did you make sure it was reliable? If you're just having it free, how did you reliably make it go 5 centimeters?
Didn't really have.
Now moving on to the preparation of the opponent. You'll have 3. All right, so to confirm, I can see that you've started screen sharing and that you have a very nice logo on the top right. So let us know when you want to start presenting, and we'll start the clock.
Yeah, so I'll start right away. Thanks a lot for your presentation. First of all, I'm going to talk about the opposition and about your presentation itself. So, of course, we have the singing ruler as our task. The problem statement is already stated, so I'm just going to skip over it if you're okay with that. It's just the characteristic sound we need to define. It's clamped at one end and struck, and then we need to investigate the relevant parameters. The report itself was really nice. We demonstrated, or you demonstrated all the phenomenon. You also, which I really liked, showed how the table itself may resonate with the ruler itself. Unfortunately, the explanation of why the ruler is oscillating could be a bit more basic, a bit more intuitive. And then also you had hand release and also no change of the clamping itself relative to the table. But we'll talk about that later in the discussion. Some parameters were only theoretically investigated, and the theory has some questionable assumptions. And more importantly, you did not talk about the initial displacement, even if you say it does not have a big effect. I would like to see what it does actually to the sound. And also, there are no clear definition of what the characteristic sound actually is. Maybe you could play it for us so that we can understand it. The experiment itself, the main point here is that the clamping was insufficient. So you said you clamped it at the end of the table, but we could see in the video that that it was not clamped right at the edge. That means you could have some kinds of different vibration modes or different vibration interactions because you can no longer assume a cantilever beam. So that would also be a question I want to ask if you're assuming in your Euler-Bernoulli equations that it is a cantilever beam. Here also the deflection was done by hand, which is why I don't really think you were able to do it reliably, but I also have some suggestions for it later. And unfortunately, you did not show us what the sound actually looks like, maybe the Fourier transform or something else. In the theory, you had questionable assumption saying that the other modes of resonance or vibration are not that relevant. We can go into that in the discussion. What I really liked was that you went over the Euler-Bernoulli beam equation with also the force equilibrium method to calculate what the frequency should be like. Clamp is still unclear because that will affect which theory you're using and which Euler-Bernoulli beam equation and how the interactions are. And also there were no mention of the boundary conditions. So when is it no longer possible? For example, your Young's modulus, after a certain amount of, I think it's 10 times the length, you cannot use it for some displacements anymore because it just doesn't work. And also, I would have loved to see the different frequencies of the different modes calculated and using this and maybe even comparing it with your Fourier transform. If you have it, you can also kind of show the twang itself. So the characteristic sound, as you actually did not mention, it's produced because you have this like base mode 1 frequency, which goes on for some long time, but there's still these higher frequencies which die out shortly. So you could have different kind of decays for different frequencies. That would also be something that I would have liked to see, but we can talk about it more in the discussion itself. All in all, I have to say that because of the clamping not being defined really well, and that's why the assumptions can't be that reasonable. We have to say that the task was insufficiently fulfilled. Also, the characteristic sound was not defined really well. And at the end, I have to say it was a good presentation, but I think it will be an interesting discussion, and I hope we can find some good things.
Let's move on immediately to the discussion then. So Z, can you move the timer forwards? Great. And you guys can start immediately.
Yeah. So my first question I would like to ask you is why exactly did you not clamp it right at the edge? And what do you think will happen if the ruler is not clamped right at the edge?
It depends on how far back you move it, because if you move it far, if you move it back far enough, then it will partially vibrate on the table, and there will be some interesting phenomenons where the edge of the ruler, as it touches the part of the ruler that touches the edge of the table, it will actually curve upwards. As the other part of the ruler that's free hanging will curve downwards. But in our experiments, it was mostly. I wouldn't say that it's perfectly clamped on the edge, but it is definitely mostly clamped on the edge. And in our experimental setup picture, I think, yeah, we just did not include the clamp, but I can assure you it's definitely clamped at the edge of the table.
Okay, I'm just going to believe you there, and you're right, there's going to be some interaction. So moving on to your assumption in your Bernoulli beam equation, what kind of a beam did you assume? Because depending on how you clamped it, you have to assume a different kind of beam.
I assume a clamped free beam, which means one end is freely vibrating and the other one is clamped.
So a cantilever beam, but
Yeah,
as we
basically.
saw in some of the videos, even though you assure us it's not really like that. It's not clamped. As you stated, you have this kind of ruler bending over the edge. And then would you agree that it has to kind of, you have an interaction of a free beam kind of being hit in the middle, which is also interacting as a vibration with the cantilever beam assumption?
I agree to an extent, but I believe like this is negligible. Like most of it's still covered by the tape on the clamp. And in our qualitative explanation slide, that was only like a preliminary setup. We did not use that in any of our testings. As you can see in that one, we used like a enlarged paperclip. When our actual experimental setup, we actually used a clamp. If you like, I could share my screen.
Yeah, sure. Please do that.
Okay.
And at the same time, maybe you could also show us, because you talked about how the frequency, the length, etc., depends on what you get out. Could you maybe show the actual proportionalities you get from your experiment and you get from your theory?
Oh, sorry, can you say that again?
Can you show the proportionalities of like the frequency dependent on the length?
Frequency dependent on the length. Yeah, this one.
Yeah, do you have a value for it? The
Value?
if you could say the proportionality, because it's right there almost.
Yeah. And I'm pretty sure the value was just taken from the first part, which is the order renewable beam theory. And for this part, I just wrote the proportionality, like for clarity, to show how it actually is proportional to the length. But the full formula is here, and the eigenvalue times length, we just take the first mode, which is around 1.8, I believe. Yeah.
Okay, so maybe I didn't phrase it quite well. I actually expected you to just say the frequency is proportional to the inverse of the length squared, because you can see it
Okay,
from.
sorry. Yeah.
Yeah, but it's all right. It would just make it a bit easier to understand. And talking about the amplitude at the beginning, why would you say that the amplitude? So what exactly will the initial displacement have an effect on our maybe on our decay?
Oh, sorry, let me go to the decay. So you're asking about the decay equation, right? I'll just move to here. So if you have a starting displacement, then obviously the amplitude at there would just an amplitude at there that point as a function of time, which is be the amplitude you give it or the starting displacement. But yeah, and like similar, like okay, sorry. Yeah, so basically this is the equation if you gave it a starting displacement. So it's modeled as cosine because at t equals 0, it will have a maximum displacement. And then it will eventually decay because of this term right here.
Yeah, so the amount of time it takes for you to go from a lot of sound to less sound will depend on how much initial displacement you have, right?
Yes, I think so. Yeah, the A is right here, so this is the initial
Yeah.
displacement.
So why did you only do experiments for only 5 centimeters? Or did you think it was so obvious that you didn't have to do it?
Wait, yeah, these were different displacements. I think I didn't write it clear enough, but these were the different displacements that I did.
Ah, okay,
Okay,
sure.
yeah, yeah.
Then that's my bad. Sorry.
Sorry.
Moving on to the modes, you only calculated the frequencies or one mode. Are you
Yes.
sure that it's only one mode of vibration? And how can you ensure that it's only one mode of vibration? Did you get like a nice sine wave?
No, as I clarified before, we try to do multiple modes, but in our experiments and when I was reading relevant papers, both confirmed that the higher frequency modes, like they will decay a lot faster than the first mode. And so even with a fast Fourier transform, they will be hard to find these faster modes. And there was not a lot of like very like how to say there's not a lot of resources I could find on how to calculate these for the higher modes and how to actually find the higher modes. So I just assumed it would be only the first mode.
Yeah. So on that part, I kind of disagree on the fact that it's so fast, the higher frequencies. Of course, if you're going to really, really high frequencies, which your microphone can't even pick up, it's going to decay very, very fast. But in the more normal range of frequencies, it's still going to be there. So you at least like 6 modes of vibration above or for base frequency. I don't know what you had for base frequencies. Let me just guess 90 hertz or something like that. You're of course going to be able to see higher modes of vibration. And for this, you also showed me kind of like a characteristic equation. And with that equation, if you put in like boundary conditions, etc., you can actually calculate the nodes which you will have. So the lambda for each node. So it's basically if you're assuming a cantilever beam, it's going to be like something like 1.8, 4.6, 7.8, something like that, because it's inharmonic.
Yeah. We also found out that like it's 1.8, as you said, the different eigenvalues. However, yeah, we were not sure how much the actual higher modes, like how much percentage of the vibration actually were the higher modes, and like what proportion they took up, how much time they took up. So yeah, as I said, and we intentionally try to get smaller displacements. The biggest one we did was 10 centimeters in the vertical direction. So we thought that was small enough where the bigger modes would be negligible.
So moving on to the part about where you just said that you wouldn't be able to know how long the higher modes of frequency would be, do you think the decay is dependent on what frequency you have?
I think the decay will be dependent on what frequency you have. I'm not sure if I don't think I characterized it here.
Right. So does that mean if you get
It will be
like
dependent on this term. This is a damped frequency.
So
yeah.
wouldn't this mean that you could get like different decays for the different frequencies of each mode you have?
Yeah, but the sound is comprised of different frequencies, but their proportions might be different. Like for example, the first mode might be 90% of all the vibrations, and the second mode only stands for like 10% of vibrations, and so on. So the proportion of each mode, they were like incredibly hard to differentiate from each other.
But
That was the main
that's what so did you do any Fourier transform? Do you have a visualization? Because that's exactly what the Fourier transform does, right? Because the vibration you have on your ruler is just the sum of all of the different modes of vibration. And the Fourier transform, it just basically shows you the intensity and all of these different modes of vibration. So do you maybe have a visualization of what you picked up with your microphone?
We did fast Fourier transform initially, and I don't think I have it in my presentation anymore, but it was really fuzzy and consistent because we were doing it in a room with it naturally had a frequency of around 30 because I did in my basement, so like there were like vents and everything. So yeah, so I was unsure about how that would affect everything. So I just did not do the fast Fourier transform.
All right, so that actually gives me a really nice transition for the end to the experimental setup and some improvements you could do to the experimental setup. Could you maybe have some kind of foam or something else in the room actually dampening the resonance in the room itself?
Yeah, because like the space I did it in was kind of big. There was no possible way I could cover the entire room with foam, and if I did it somewhere else, it would probably be louder. Yeah.
Yeah, so I didn't mean the entire room, but just maybe like a somewhat big box where you can put it in. Other than that, did you maybe look at how you could make the initial displacement be equal? And do you have any idea of how you could agitate the ruler just with your hands? My suggestion would be you have the ruler and then another ruler at the perpendicular at the bottom, and then you can always have maybe with like a line, you can somewhat see how deep it is going or not.
Yeah,
Right?
that's essentially basically what we did, but we just had the ruler like somewhere here, I placed a ruler perpendicular to it, and I would see how much I flick it. So it
Okay.
was not, yeah.
Yeah, and also the different notes, won't they be dependent on how you actually touch the ruler or make it vibrate?
Yeah, I try to make the vibration like as standard as possible in the sense that I try not to displace it past it. So I would just place my finger, for example, with displacing it 5 centimeters, I would just place my fingers on the 5 centimeters mark and I'll push it like parallel to the ruler, so it will not cause it to vibrate up and down any further than the 5 centimeters.
Right, we're out of time now, so we'll move on now
Thanks.
to the opponent remarks. You have 1 minute for remarks. Yeah.
Yeah, so it was a pretty nice presentation and also a pretty nice discussion. I think we were able to clarify some of the initial assumptions and initial characteristics of how the experiment was done, etc. I especially had to talk about how it was clamped itself, because depending on the clamping, you have to use different Bernoulli beam equations, which will give you different results at the end and different frequencies. What we especially missed was the fast frequency transition. I can understand fast Fourier transform transform, I can understand that you were not able to do it, but maybe with a better experimental setup and more dampening around the room, I think the resonance shouldn't be that much for all the modes. You said it was 30, so maybe the bass one has a lot of resonance. So maybe this is something you could look at later. Also, you would need a better kind of experimental setup to ensure similar agitation of the ruler each time, because depending on how you agitate it or how you make it bend, it's going to have different modes of vibration being agitated differently. So all in all, I think it was a good presentation, but the tasks, I still say it's
Sure.
insufficient.
Let's move on now. You're out of time. So for the reporter, you'll have two. Sorry, Z, can you read out the phase? This is the. Can you pause the phase real quick? 1 second. Let's move on. So this should be. Oh, sorry. This is questions from the reviewer, I believe. So the reviewer, please ask. You have 3 minutes to ask questions.
All right. Hello, I'm Isaac from Team Shroomskis. And I guess a first question I have for the opponent was, how exactly did you model the boundary conditions for the ruler?
So first of all, we have that the ruler length and the displacement, there has to be a relation which is not more than 10 times. And then after that, I just assumed a cantilever beam and then said at the fixed end, we have F0 or no displacement and no rotation. And at the free end, we also have 0, 0. So that were my boundary conditions.
Yeah. And another question I have for you is that since you were talking a bit about like the initial displacement of the ruler having an impact on the amplitude or possibly frequency, what do you think the effects of the initial displacement would be on the ruler?
The initial displacement is just the starting amplitude, so maybe the loudness and how long it takes to delay, because at the start you have more energy and then it goes off. Yeah.
Okay, thank you. And I have the next questions for both the reporter and the opponent. It is like the reporter had assumed like the end of the ruler was rigid, right? That it was perfectly clamped, and you guys talked about this. How do you think this affects the actual ruler's motion if it was not perfectly clamped, and what sources of error could have resulted from this?
So who wants to go first?
Yeah, I could go first. So if the ruler is not perfectly clamped, obviously it will rattle at the clamped end, and some of the boundary conditions will obviously no longer be valid, and so that would be one source of loss. So, like, yeah, that's pretty much what I want to say.
Yeah, so if it's not clamped really well, you cannot assume a cantilever beam anymore. You have to assume some interaction within a free beam getting struck at the middle, which changes your Euler-Bernoulli equations and also the kind of modes you get.
Yep, thank you. And my next question is for the reporter. So in one of your slides, I think it was like very early on, your model assumed the sound intensity of the ruler was spherical. And do you think the ruler was actually a spherical or isotropic source? And do you think this assumption is actually valid, or would the effects be negligible?
I think it will be a spherical source, because if you think about like any wave propagating through the air will obviously travel in a spherical fashion if there's no sort of like, nothing blocking it on the sides or anything. So yeah, I think all the other effects will be negligible.
Yeah, and just did you confirm this at all, or is this just like your assumption? Like, do you know that like at all points at the spherical, it is spherical?
We did not do any experimental testing with that, so it
Okay,
is just an
thank
assumption.
you. And to the opponent, do you think you agree with what the reporter is saying?
I may have to agree. Yeah.
Yeah, okay. And I guess I know you guys talked a lot about the assumptions. Um, do you think like do you
Sorry,
think the
we're over time, so I think we
okay.
have time to finish this.
Yeah.
You now have 2 minutes for the preparation for your report, reviewer. So you have 2 minutes to prepare. Sure. So for the review, your time is now over. Please share your screen as fast as possible. Yeah. Sure. If you don't have a report, you have 4 minutes to take the floor. And that will start now. Yeah.
Can everyone see this? Okay, thank you. I'm Isaac from Shroomskis, and I'm going to be reviewing problem D, singing ruler. Like the opponent and the reporter previously mentioned, I don't think we need to repeat the problem statement. So, okay. So, some tasks that we outlined for the reporter was to build a reproducible and stable experimental setup. This was pretty well done with a few concerns that we had. The task 2 was to qualitatively analyze the phenomenon, which we thought was good. Task 3 was to quantitatively analyze the motion of the ruler, which was pretty good. And task 4 was to investigate the relationship between the parameters, which we thought was pretty well done. So just give a brief summary of the report. The theoretical analysis had started with the Euler-Bernoulli beam theory. It also covered damping and then moved on to some acoustic characterizations of the ruler's motion. And then in terms of experimental confirmation, we had some characterizations of the Euler-Bernoulli beam theory and other constants, as well as experimental verifications with frequency and amplitude, and as well as parameter variations. So some merits for the reporter was that they had some pretty good quantitative characterizations with both the Euler-Bernoulli beam theory as well as their acoustic models. And then they also had a pretty rigorous experimental setup, but they had a few concerns with that, which I'll talk about later. And they also had a very detailed theoretical exploration of almost all aspects of the ruler's motion. So some concerns that we had with the report was that it labeled the experimental setup a bit flawed in some cases and did not have full transparency for all aspects of the experimental setup, which was partially covered by the opposition. And they did not really show, let's say, the fast Fourier transform and the cantilever beam being fully clamped down to the desk. There were also a lack of boundary conditions in their theory, which we had concerns about, but the opponent had already addressed this. And there was also a lack of transparency in the sound data analysis, as the fast Fourier transform was never shown. The rest are more things that we'll discuss later. So just to give a brief summary of the opposition first questioned the experimental setup and how reproducible it is in terms of the clamps, the release mechanism, and the damping. The opposition also questioned the theoretical characterizations, with being the type of beam for the Euler-Bernoulli beam theory, and the cantilever beam, and whether or not it is valid for this case, and the lack of definition of characteristic sound. So for the opposition, some merits that we found was that they clearly outlined their concerns. They had good recognition of experimental setup errors, and they also had excellent points highlighting the lack of analyses for higher modes. Some possible next steps was that there was some a little too much focus on less significant points, such as the clamping effects and the cantilever versus free beam theory, which we thought they could have skipped over in more time and moved on to other things. And the slides did not highlight discussion topics. So just to give a overview of the discussion, they started with the type of beam being used with the Euler-Bernoulli beam and how it was unclear, but the reporter clarified that the assumption that the beam was cantilever beam is sufficient, and we do agree with the reporter here. The next is that the effect of the initial displacement of the ruler affects the decay, and the reporter replied that the effects of the decay at a somewhat linear rate, and we agree with the opponent that the initial displacement is important, but not especially important for frequency. And then another thing that was covered was different modes for vibration is significant, and the lack of Fourier transform sort of highlights this. And the reporter responded that it was difficult to detect higher modes due to fast decay and ambient noise, and we agree with the opponent that higher frequencies and different modes are detectable and should be considered. And the last concern raised by the opponent was that the reporter could have added foam or other materials that could have dampened the resonance of the room. And we agree with the opponent here that a black foam box might have been more ideal.
You're out of time, so please stop the presentation. And then see if we can now move on to the next phase. The next phase will be concluding remarks from the reporter. The reporter has 2 minutes to make any concluding remarks. Thank you.
Okay, I thank the opponent and the reviewer for an excellent, fruitful discussion, and I would like to, and we had a lot of points where we agreed, like, yeah, but there's also a lot of points that we did not agree on, which I would like to address now. So, mainly the opponent and the reviewer, they talked about the lack of boundary conditions, And I would like to say that I had boundary conditions for the damping cases for both the initial impulse and an initial displacement. However, I did not really include the boundary conditions for the cantilever beam, as it was derived in many papers, like the ones that we found in the student reference kit. So that's why I did not really put it in the in my presentation. And next, we did not show the fast Fourier transform. Obviously, this was a a problem on our part, and if we were to continue doing this, we'll absolutely like try to make the sound more pure in the sense that it was separated from the ambient frequency of the room. And we will try to find it for our next step. And obviously, for our qualitative explanation, I thought that we clarified and we explained a large part of how the sound is actually produced from the table to the ruler, but there's clearly still some confusion or on how the sound from the ruler is actually produced, and it's just like when the ruler vibrates, it's able to disturb the air and it's able to create like this longitudinal wave that compresses the air at some points and compresses it, which creates like obviously a sound wave, and that is yeah, that is how it works, basically. That's all I have.
Well, if you have nothing left for the last 20 seconds, we can just move directly on to the juror questions. So jurors, since whoever has a question, you can first speak up. If there's too many of you, we'll go through you one by one. So yeah, you can start the time scene. Again, so if any of the jurors have questions, go ahead.
Yeah, I think I can start. Two very quick questions. So, reporter, in your images, I saw there's like this white bin / box under the ruler. Was it that there for any reason, or?
Sorry, so question directed to me.
Yeah.
Okay. Like I did not address it. I kind of forgot the point, but like we could not find a box that was large enough to cover it. And yeah, because the experimental setup was roughly like 2 tables long, which is around like 2 meters long. And yeah, we didn't really see a point of constructing like a setup to cover it just for the purpose of separating it from the ambient frequency. And we did not have enough time for that.
Okay, and quickly to the opponent. So we talked a lot about Fourier transforms. Did you guys actually do a Fourier transform? Did you manage to see some higher modes?
Yeah, I was not quite sure if we can have our own results in this or not, but I had a result where I could calculate up to the 6th mode of vibration. And it also went to something like, I think, 900 hertz, depending on the ruler.
Okay, thank you.
Okay, for the opponent, Ayush, you were asking the reporter about a different model for the beam. What kind of like theoretical, aside from Euler-Bernoulli, what other model would you use?
So it would still be Euler-Bernoulli, but from Euler-Bernoulli, saying that our solution is going to be some temporal differential equation multiplied by a spatial differential equation, you get a kind of like a characteristical differential equation in the spatial part of it. And it's going to be different for a cantilever beam, this characteristic equation, and the nodes you get, and it's going to be different for a free beam, which is getting hit in the middle. And this is the interaction I was talking about, because if the ruler is just really clamped at one end, you of course have a cantilever beam, and this works. But if the ruler is hitting the edge of the table now and again, you could kind of imagine it like a free beam getting hit in the middle. And then you have to kind of find out the interaction between these two different characteristic. Yeah.
Okay, thank you. Akash, your turn.
Yeah, you guys have already had some good discussion on the number of modes in the harmonics, and you restricted it to 1. So I was wondering if you can point out a few parameters which might have got an influence from the assumption of a single mode harmonic.
So I think the most obvious one would just be the frequency, because obviously if we were to include the higher modes, the frequency will be a mix. So it will obviously result in a different one. It will probably be a higher frequency because higher modes, like they vibrate with a higher frequency. And also the eigenvalue will be different in the Euler-Bernoulli beam theory. And it will probably, like, it will be a summation or like some sort of combination of the different modes.
Okay, what do you think about the VRMS assumption that you have had
Oh,
with this
yeah.
single mode? Yeah.
Sorry, let me go back to that slide. So the VRMS is, sorry,
Again,
let
you have
me,
assumed the root 2 in the denominator, right? Which means a single mode.
yeah. So I think that will probably also be different.
So how is it gonna affect your result? That's my main question.
So it will probably make the VRMS slightly faster if you include the higher modes.
So it will be
Because
underestimated?
the angular frequency term omega will be higher.
Okay,
Yeah.
okay. What do you think, Ayush? The same question to you.
So I didn't quite follow on the RMS, but I would say that if you no longer have, if you don't differentiate between all of the different modes, you will have the base frequency actually be higher because I wouldn't expect the other modes to deconstructively interfere with your base mode.
Okay, thank you.
Sure. Can we get Matt to ask a question? And then
Sure, thanks. This is to the opponent. I was just wondering, you had talked a lot about the cantilever or free beam action of the ruler, and I was just wondering how did you deal with this? Is this something that you thought about when you were doing your own experiment? Did you use that alternate form, or did you do something else? Thanks.
So I just used the cantilever beam form by really ensuring that it was clamped right at the end using strong enough clamps, or in a case of a metal ruler, electromagnet, which held up to 680 kilos, I think. Yeah.
Awesome. Thanks.
sure, I think if there's anyone who has a burning question, you can ask. We're pretty lax in terms of your question timing. But if not, go ahead.
I have a question for the opponent, if there's still time. So I had a follow-up to Osama's question where he asked about the frequency dependence, right? And so I was wondering, like, did the frequency fall off? Like, do you have an idea of how the frequency fell off as the mode increased, like either 1 over n or like 1 over n squared or something like that?
Yeah, 1 second. I have to kind of find the factor I had for it. So for my dampening itself, depending on the different frequencies, I had a decay rate, which was then pi into the frequency divided by Q, a quality factor.
Sure.
So
let's stop.
the higher frequencies decayed faster than the slower ones, which went on a lot longer.
Right. So we're a bit over time now. So can we get the jurors to please upload your score sheets to the drive? So for finals, for people who don't know, we don't declare the scores until after the finals. So that there's some added element of suspense. So yeah, we'll be after the finals, you guys will know, I suppose, when we announce the winners. So if all the jurors could please upload your score sheets, and once you have uploaded them, please raise your hand so that we can confirm you've uploaded them. After that, we'll move on to the next round.
The suspense, it's killing you.
Right, the suspense. So the next presentation will be Germany presenting Ring Fountain, and Shroomskis will be opposing this, and Team Excel will be reviewing this. Right now, I believe that we have 7 score sheets in the drive. 6, sorry. So we're waiting for 4 more jurors to submit, and then we'll move on. Seems that some of the teams are very excited based off the cameras. Yeah. 7, 3 more jurors. Meanwhile, Z, can you reset the timer? You can just reload the tab. And then right now we're missing 2 more jurors. So for the jurors, we are still missing 2 jurors. So if you are one of the people who have not yet uploaded your score sheets, please upload to the score sheet to the drive. And then we can move on to the next round.
I think all the jurors have their hands up. Oh, no, I can see some that don't. Okay.
Yes, yeah, I'm missing 2.
Sorry, can you just repeat who's going to be doing each role for this match, please?
Sure, absolutely. So for this match, the reporter will be Team Germany, and they'll be reporting Ring Fountain. The opposition will be Team Shroomskis, and they'll be the opposition. And lastly, the reviewer will be Team Excel.
Okay, thank you.
It's no problem. Okay, we have 9 jurors now who have submitted, and we are lacking the last one. Sure. So I think Akash, are you there?
Yes, I'm here.
Have you uploaded your score sheet yet? I think you might be the last.
No, I have already uploaded.
Okay. Oh, you've already uploaded. Have you uploaded it to the right folder? Sorry, what is your...
Yeah, I did. I can see mine with the others.
I think, oh, okay. We're still missing one. Let's see. Where's the odd one out?
1, 2, 3, 4, 5, 6. But all the jurors have their hands up. But then
All of the jurors have their hands up. Oh no.
Probably someone uploaded to the wrong folder. Let me double check.
Sure, we can check for you.
Oh, this is very humiliating for jurors to make this mistake.
It happens all the time. Don't worry.
The jurors need to get a penalty.
Right, a pay dog, right? We're still missing one. So everyone can just ensure that they've uploaded it to the CaYPT 2026 scores, day 2, and then the finals folder.
Sorry, there are a few score sheets that doesn't have their names on it, so I can't really tell who gave the score sheets.
But you can see the owner. Like I see Tan Ferreira, myself.
You can see the email of the owner.
Abhinav, Gaurav.
Maybe the teams are enjoying the extra time to prepare. So
yes.
Tosh is here, and who else? Yeah, she's here. I don't see Matt. Yeah.
I
see Matt. Yeah.
I did
right there.
The cardinal sin of not putting my name on it, but yes, I have.
Yes, I see Forbes.
Wait, then what? Then
Yeah, I only see 9 names.
I only see 9 names as well.
Oh my God.
So frustrating, man.
So let's hunt down the juror, I guess, in nicer terms.
Another juror.
Wait, we have 10 jurors, right? Just to be sure.
Yes, we have 10 jurors.
It's gonna be so jokes.
Yeah, she's here. What? 1, 2, 3, 4, 5, 7, 8, 9. But wait, there are only 9
Yeah,
jurors
so
in this chat.
I don't think Utkarsh is here.
Oh.
Wait, Akash is here though.
Utkarsh.
Utkarsh and Akash are different, and when
Oh.
somebody calls out Utkarsh, there's language Akash.
Yeah. Utkarsh is not here. Wait, what?
Right, Utkarsh isn't here.
But Utkarsh in the group chat confirmed that he would be here.
I thought when we were checking the names, like he was here, but okay. 9 jurors.
Okay, 9 then.
I guess we continue with that.
Okay.
So in this case, we will now move onwards.
Okay,
Yeah,
sure.
let's move on.
Yeah, let's move on then.
Sure. So well, this time it will be Team Germany presenting once again, and they'll be presenting Ring Fountain. So Z, can you please start the preparation timer for Team Germany? Or you can skip the skip these 2 phases. Cool. Thank you. And yeah, good luck.
By the way, if for whatever reason Utkarsh decides to come back, we can't have him give grades. He can watch, okay? Because, yeah.
I'm surprised no one mentioned the Timoshenko beam theory in the previous round.
Oh yes, I was waiting for that actually.
Yes. I was waiting for that too.
I
think
didn't
it was
see
a
it.
very leading question, right? Someone asked, like,
The
what type of
different
beam
beam
theory would
model. I
you?
thought someone was gonna throw Timoshenko, but like,
Yeah.
oh,
No,
okay.
shout out Timoshenko, right?
I see we have Russian sanctions.
we simply need a larger angle beam model at this point.
Or a thicker beam.
Thicker beam, so small angle approximation is doable.
Yeah.
All right, so Team Germany, if you want to start presenting early, you are more than free to, since we have had some delays. Yeah, I'll take that as a no. They can have their 5 minutes, I guess.
Okay, yes, so I would be ready to start presenting.
Z, are you ready to move the timer onwards? I guess. Okay, cool. The timer has been moved onwards, and you can start when you want to. You can start now.
Hello, my name is Arn. I'm from Germany, and I'll be reporting on task F, ring fountain. When a flat metal ring falls from a certain height into a water tank, it generates a fountain that can shoot water high into the air. How does the maximum height of the fountain depend on the ring's parameter? On the right, you can see a video displaying the phenomenon. As with most videos in this presentation, it was recorded at 1800 frames per second and is played back at 18 frames per second. Now for a short overview of my presentation, starting with the experimental setup. In order to drop the metal ring, an automated release mechanism was used. The main element here is an electromagnet with an iron core, which prevents the metal ring from falling. This electromagnet is attached to a 3D printer head using a 3D printed magnet holder. As soon as the metal ring is released, it gets additionally stabilized by a 3D printed rod during the first stages of its drop. To release the metal ring consistently, we need to control the electromagnet, which is why we use a Arduino relay connected to our PC controlling setup. And for the high-speed videos, we use a high-speed camera filming at, as mentioned, 1800 frames per second, as well as an LED for a backlight to illuminate the ring and the ring's behavior from behind to observe the fluid's behavior. So as you've seen, the release mechanism is attached to 3D printer head. This prevents the upward jet, which is often so fast that it reaches heights over the initial drop height, of hitting the release mechanism, which would interfere with our results. As you can see in the real-time footage, these two events happen very quickly after each other, which is why we need precise synchronization in our setup, for which we use a Python control script. So as we're now capable of dropping such a ring, we're going to ask what happens after such a drop, beginning with our qualitative overview of the phenomenon. In freefall, the ring is accelerated downwards due to gravity. As soon as it reaches the water surface, the ring will induce a hollow cylinder of high pressure below itself in the water, which will push the liquid both in and outwards. Now, switching to the top view, we can see that the displaced water again is traveling on the one hand to the outside and on the one hand to the inside. We'll now focus on the inward motion and see that the water carrying the fluid carrying the momentum of the water converges to one single point. Here, the radial momentum will cancel out, and this is then transformed into the upward momentum. This is the driving phenomenon, which actually induces a first upward jet in our experiment. And indeed, in the videos, a high-speed jet can in fact be observed, but we also see water displaced outwards. This water forms a corona and an air cavity develops. Focusing on the cavity further, we see after it starts to collapse, water starts flowing inwards again. Water is then present in all the marked regions. And just for comparison, our numerical simulation yields relatively similar qualitative results. Now, observing the two surfaces approaching each other, one might think of a so-called Worthington jet. In the right figure, which is taken from literature, we can see how such a jet is formed. This happens when the cavity collapse of the momentum, when we have two sides of the momentum forming an upwards and downwards jet. A similar mechanism is acting in our setup, however, with a key difference. The water does not collapse in a single point, but the cavities do not collapse in a single point, but rather in a circle. This is why, when we observe a so-called second jet in this case, this has a more irregular, almost cylindrical shape, we could say. And it mostly does not reach the height of the first jet, except in some extreme cases in theory. So now let's go on to the theoretical observations. And as we've understood the underlying processes of this phenomenon, let's move on to the identification of the relevant parameters. First of all, we have to represent the geometry of our ring. This is represented from the inner and the outer radius. And apart from this, the most important parameter is the ring's velocity at impact, which is caused by gravity, as well as the ring's initial release height. Now, for the water itself, we have the density. Besides, we also have the viscosity, as well as finally the surface tension of the water, which is relevant at the contact point. Now, as the Buckingham Pi theorem states, these 7 parameters can be rewritten into 4 dimensionless numbers. These would be the Reynolds number, the Froude number, the Weber number, and the ratio between the inner and the outer radius of our ring. Now, keeping these numbers in mind, we can move on to the theoretical foundation of our simulation. So in order to model the fluid behavior, we have to regard 2 main fields. On the one hand, we have the velocity field, and we have the second one is a fraction function, which will keep track of the fluid's distribution. If the fraction function is 1 at a given point, this point is water. Otherwise, the function will have the value 0. Now we have three further equations we can state to solve the system. These would be the transport equation, the continuity equation, as well as the dimensionless Navier-Stokes equation, for which we dimensionlessized our previous parameters. And looking at the coefficients of said equation, we observe again the three dimensionless numbers we obtained previously. We can now take this numerical approach and solve these equations using the fluid simulation tool Basilisk. For this, we use adaptive grid refinement and assume the velocity of the ring to be constant. At this point in time, the simulation is not well optimized yet for our phenomenon and does in fact not have a full amount of prediction power. However, still we have to keep in mind, that the most important parts are still observable. We have mainly the first jet forming from the displaced water. We have the bulging in and out of the water cavity, as well as the second jet which forms after the cavity collapse. After this point, though, the simulation yields some unexpected results we have not seen in experiments. So we might ask ourselves how these individual processes depend on the relevant parameters of our setup or of our experiment. So let's continue with our experimental results. At first, we'll compare different impact velocities of the same ring. The videos are synced up so that the impact occurs at the same moment. And as the videos have a lot of things happening in them, it's important to try to focus at on the cavity formation and collapse at first. In all three experiments, the cavity collapse happens at the same time, from which we can experimentally deduce that the time of cavity collapse is probably independent of the impact velocity of our ring. For the next observation, we will watch the same three videos again. This time, though, they have been adjusted so that the impact velocity appears to be the same. This basically just means the impact velocity, the highest impact velocity video, so the one on the right, has been slowed down the most. And in this case, let's observe the first jet formation, the one which is caused by the water displacement. So as you can see, all three jets seem to be equally fast, as in the adapted time, they appear to have the same height. Therefore, it follows, since we have the adaptive slowing down of the videos, that the velocity of the first jet is directly proportional to the velocity of the ring. We can also make this more clear using a simple plausibility argument. We'll look at a very small time step delta t after the ring's impact. As we've seen, the water will form a beginning corona and a jet in the center. But as the ring sinks below the initial water surface, here marked in red, it will push away a volume V0. Now this volume only has two possibilities where to go, either towards the outside, being a part of the corona, or forming the jet on the inside. Computing the two volumes using simple geometric, but we can now also further assume that a constant fraction of the volume lambda is pushed towards the inside. And after this, we can compute the two volumes using some simple geometric predictions, geometric properties. We can obtain the equation, or an approximate qualitative equation, describing the relationship between the jet of the first jet's velocity as well as the impact velocity of the ring. And now this is not sufficient for further theoretical predictions, but the simple plausibility argument does indeed show the linear relationship we can also observe in experiments. Furthermore, we could also technically estimate the maximum height of the jet using this initial velocity. But let's look further at different regimes of behavior in this experiment and in this phenomenon. If we try to approach the limit of very low velocities, we can observe that the most important elements of the process still occur. We will observe a first and a second jet in the video. However, they will not reach the same height to width ratio as in the previous experiments. Thus, they will show different behaviors such as interesting drop detachments. Varying the radius, we can also see that the ring with a very small inner radius on the right, the first jet of this ring will break up into a lot of smaller individual droplets. This is the general behavior of thin liquid jets, which break up into droplets due to initial perturbations from noise. The particular wavelengths caused by these perturbations will grow until the jet breaks. This is also, by the way, the driving phenomenon of last year's CaYPT problem, dripping fossils. This is why at the point of collapse, there is no relevant jet stopping the cavity, from which it follows that the cavity collapses again in a single point. The difference is clearly visible. On the right, we have a classical Worthington jet, whereas on the left, we have something different, which means there seems to be some kind of threshold, and this hints at some kind of interesting regime transition and areas of further research. But for now, let's conclude. We presented a sophisticated experimental setup capable of capturing high-speed videos of all relevant mechanisms of the phenomenon. For these processes, a qualitative explanation was given, as well as a numerical ansatz for the theoretical parts. On the experimental side, proofs of the effect of the most important parameters were given, and in the end, different regimes were observed, hinting at interesting regime transitions. Thank you for listening.
Right, you're exactly on time, so let's move on immediately to the rapid fire from the opponent. The opponent, you have 2 minutes to ask rapid fire questions. See, can you progress? Okay.
Has the time started? Yes. Okay. My first question would be, did you measure like the depth of the tank that you used, and would you believe that if the depth was lower, that the effect of the coin hitting the bottom would affect the pinch-off behavior?
I don't believe the effect. So we haven't measured the depth of the tank because we believe that the pinch-off is independent of the contact at the bottom, as the pinch-off happens above the cavity collapses above the coin and not below the coin. Oh, the ring. Sorry.
You also mentioned that or it seemed like in your video at least that the coin seemed to be a little bit angled upon impact with the water at some points. Do you think that this translational motion might affect your results or possibly?
Yes, we can go just a bit deeper into the experiment. I believe so I think the maximum height, the effect will be negligible. But I think you could have a very, very slight effect, yes. But I think the effect you see is negligible. In fact, you can go deeper in the discussion if you want to.
Sure. And you also mentioned that there were multiple differing regimes depending on whether you dropped at a very low height or not. Did you characterize theoretically where this boundary might occur?
No, we have not characterized this theoretically yet.
Cool. Also, do you think that there's a relationship between the thickness of the coin or only between the size of the coin and the inside hole of the coin?
I think you will have some kind of limit if you have an extremely thick ring. But the first jet we believe is mainly just formed from the impact itself, so from the bottom surface, and the second jet's cavity collapse happens above the ring. So as long as it's not some very thick, as long as it's not a very thick ring, we believe it won't have an impact.
Sure. And do you believe that the specifics of the ring, other than its surface and its mass, have any effect? Like, for example, the material?
Please answer and then we'll finish.
They could have a slight effect, yes, maybe on the cavity shape or the stickiness, effectively.
Okay, sure. Let's move on now to the preparation of the opponent. The opponent will have 3 minutes to prepare the presentation. So opponent, you have 30 seconds remaining. You may want to start sharing your screen if you haven't. So opponent, your time is almost up. Make sure that you're sharing your screen.
Yes, we're going to share the screen. Open your camera. Oops.
Hi, are we audible?
Yes, you're audible.
Why is,
You
why
can
is the
start
computer
now.
cooked?
Why is
Are
it
we
cooking?
audible?
Yes, you're audible.
Okay. Oh, it's fine. Oh, just kidding. Stop that. Wait. Wait. Okay. Is the timer started? I can't. Yeah. Okay. So hello, I'm Jeff with Shroomskis, and we're opposing problem F ring fountain. So for this problem, um, we have four main tasks. The first is to build a reproducible and stable experimental setup, which we believe was well done. We also have to qualitatively analyze the phenomenon, which was good, and quantitatively analyze the maximum height of the fountain in particular, because that is what is asked of you in the problem statement, which we believe is well done. And finally, to investigate the relationship between the parameters that we are looking at. So overall, in the qualitative, oops. Overall, they provided a strong qualitative explanation. They gave a theoretical model based on Navier-Stokes and solved it numerically, and they created an experimental setup, dropping the coins of differing hole size, different size from different heights, using their 3D printer setup. So the merits of their approach, we believe they had a good qualitative explanation of the phenomenon. Their Navier-Stokes simulation was impressive, and they had a good experimental demonstration. They also had a good qualitative description of the relationships between the parameters and the regimes, and the presentation was overall easy to follow and well-paced. We do have some possible next steps to offer, however. We have some concerns regarding the experimental setup. There was a little bit of lacking in the experimental and theory verification with each other. There was a slight lack of analysis when it came to the drop height and the ring thickness, not only the ring size and the ring hole size. And there was not very much, there's not any characterization of the regime thresholds, even though they were observed experimentally in the theory section. So overall, during the discussion, we have a few points that we want to go over. First are the shortcomings of the Navier-Stokes simulation and how they might be explained, or how we might come to understand the differences between that simulation and the experimental results. We'd also like to talk about possibilities on how to characterize those regime boundaries in the theory. I'd also like to have some discussion about some specifics of the experimental setup. And finally, we want to talk about the major points regarding thickness of the coins versus the cavity size, and the drop height.
See, can you move the timer forwards and they can start the discussion? You guys can now start the discussion. If you can get the report to screen share maybe.
Yes, 1 second.
Are we good to begin?
Yes, the timer has already started. You can go.
Cool. So I think you acknowledged it yourself in your presentation, but while like some of the broad strokes seem to be present in your Navier-Stokes simulation, especially near the beginning, I think you acknowledged yourself that at the end there was some odd behavior in the simulation. And obviously it is difficult to simulate all these particles with all these degrees of freedom at the same time. So what do you think like happened? Why do you believe that there's a discrepancy,
Like,
especially at the end?
you mean the main discrepancy in the end, why the behavior is so unexpected?
Yeah.
Okay, so this is basically this is due to an assumption we made in the theory. So we assume in the simulation that our container does not have a bottom for our ring, which is traveling at constant velocity, but it does have basically a fixed bottom for the fluid. So when we extract the ring, we will just create a negative volume, which will then create an additional impulse, which is then transferred into this transverse motion upwards and then creates this unexpected behavior. It's just basically it's based on a missing boundary condition of the ring being able to stop at the bottom.
Sure. So how do you think that the fixed bottom of the fluid would have affected the jet, and how can we go about simulating that using Navier-Stokes?
So I think the main. So I think again the main thing which is happening here with the simulated the shortcomings of the simulation is based on the fact that the ring is in fact not being stopped by the canister. So if we simply stop this, we won't have this basically this third jet forming and shooting upwards to the middle, which is where we believe our theory basically or this application of our theory will fall apart.
Sure. I mean, I guess another thing that I was wondering about is that the problem statement specifically asks about the height of the jet and not necessarily about the other conditions that occur after the primary jet. So, like, I was wondering about sort of like the relevance of the next few jets, especially when you acknowledge yourself that the following jets would not reach the same height or the same velocity that the first one did.
Sorry, you mean like why this? Can you maybe repeat the question? I'm not quite sure if I understood.
Uh-oh.
Hold on. I'm sorry about this, I think.
I think the computer we're using has died.
Yeah,
Did you hear the last
question?
If I understood, like the why the height of the second jet is smaller than the first jet, did I understand it correctly?
Not quite, like as in why, like you acknowledge yourself that it is not, it is a lower height, both in theory and in your experimental results, right? So,
Yes.
given that the problem statement is primarily concerned about the height of the jet, would it not be more useful to sort of characterize the first jet rather than attempting to create a simulation that can accompany this wider range of condition?
Well, I think I guess in that regard I would agree, but I think we just have made a generally applicable simulation which can show both results. Of course, if we're observing the maximum height, we will primarily observe just the first jet, except in some theoretical extreme cases.
Sure. I mean, like I guess this goes like to a more core point, but like what would you say is like your answer to the actual problem statement? Like how do you what would you say if I asked you how would you maximize the jet height? Like what are the dimensions of the ring that you would use?
So I would use primarily I guess like a relatively large ring surface. Basically just the ratio between the inner and outer radius should, in theory speaking, like approach zero. If you would not have the Rayleigh plateau instability where the jet breakup would happen, this is where you would theoretically, we believe, measure the maximum ring height, as you'll push the most amount of the most amount of water either outwards of the corona or inwards towards the jet. So I guess a very wide ring with a very small hole would be our answer to the problem statement.
Right, but all the experimental simulate or all the experiments, not the simulations that you have done, have been sort of more concerned about specific parameters, but also not necessarily with the height itself. Like I don't believe that you ever actually measured the height of the jet. So obviously there's a theoretical answer, but did you have an experimental result that you believe would demonstrate this theoretical prediction?
For the specifically small rings, this is experimentally not easy to verify because of the jet breakup, but we believe that the velocity of, like the exit velocity of the primary jet, which is the faster jet, will correlate to the maximum height. So if the jet is faster, we can verify this experimentally, the height would be higher. But I guess to answer your question, no, we have not characterized specifically the height of our jets, more the velocity.
Have you done so even in like in simulation though? Like even if it wasn't possible to do it experimentally, you have done simulation and the simulation have provided results. So is there like sort of like a number you can provide, I guess, for how you would say the result should be?
No, in this case, we don't have such a result, no.
So it's more of just like a qualitative relationship rather than a specific
Yes, again, I guess in that case, yes, but we still believe that the velocity of the first jet will directly affect the height. And if we can maximize this velocity of the first jet, this will also maximize the height of the first jet.
Sure. I would agree with that. Um, I think this is also going back to the sort of rapid fire questions, but the rings, it all that's specified is that they're metal rings, right? It doesn't really specify anything else about them, like the thickness or the what's it called? The material. So that they would even though they wouldn't affect the actual surface of it, and even if we discount the effects of like drag or the effects of the boundaries, um they would still have effects on at the very least the mass and the momentum that the ring has, right? So how have you explored the varying density of the rings or the varying thicknesses of the rings on the jet heights or regimes?
At this point, we have not explored the variation of thickness. We believe that for the first jet, the primary driving mechanism is in fact the impact velocity and not the impact, the impact velocity, which will create the pressure cylinder below the ring. And for the second jet, we believe that the mass would probably have an effect based on how quickly the cavity would collapse and how large it would grow. But since the second jet does not have reach heights comparatively as high as the first jet, we believe that this is therefore negligible or an acceptable negligence.
I mean, there is something to explore though, right? If it might be possible that given a sufficiently thick coin or a sufficiently dense material, that the second jet would begin to approach the height of the first jet, right?
Maybe, but we believe this is mainly the height of the second jet will mainly reach the first jet when we basically weaken the first jet. We can go into more detail when this should happen. Like we have a kind of a line of argumentation when this would happen, but we don't believe the mass would be the most important factor here.
Sure. I mean, there's also the thing about the drop height. Obviously, you did vary drop height. There were some drops that were from just barely above the surface of the water, and some drops that were higher. But there were never really drops from a sort of a more extreme height, like half a meter or something even more than that. Like at the point where it's not so much about just the velocity, but there's also like air effects, and the impact velocities are just higher in general. Did you guys have any experiments regarding sort of these more extreme drop heights?
No, we were basically limited from the 3D printer height in our experiment. Also, this would be maybe a bit harder to control the flatness of the ring if you have it dropping through the air as much and not having a long enough stabilizing rod. I guess you could extend it though in this case. But no, we have not done experiments from extreme heights yet.
I mean, I was just imagining if the material is not really of concern that like a magnet might suffice.
Yeah, I mean, I guess it would. And the expected results would just be that the jet would be higher proportional to the impact velocity.
Sure. So there was like an equation that showed up briefly that predicted the correlation between impact velocity and height, which to my understanding was just a result of the kinematic equations. Do you think there's something more to be said about that, like whether the velocity or yeah, so the height of the jet is velocity squared over 2g, which is at least it seems to me to just be a result of the basic kinematic equations. Do you think there might be
Yes.
any other effects that might influence the jet height other than just a physical sort of like gravity accelerates it downwards and that's it?
I mean, you'll have, I guess, some kind of surface tension effect in the jet itself, I guess, which were not accounted for. This was more of a plausibility argumentation in this case.
So if I understand correctly, then the majority of the experimental and theoretical work was sort of more oriented towards the velocity, and this is just sort of taken as a given and extrapolated to the problem statement.
This was more of a plausible, we basically showed experimentally that the velocity would be proportional to the impact velocity, and the first jet's velocity are proportional to each other. So we basically just wanted to we're trying to argue why this would be the case, why we believe this is a valid result or valid conclusion.
Yeah, I mean, I think we agree that it's proportional, but I think there's like sort of something to be said about some more ex theoretical experimental verification to confirm that the relationship actually exists.
Yeah, I agree.
Do we maybe just something really quickly? You mentioned the jet formation regimes, but you talked about how you didn't have the time to characterize the regime boundaries of the jet braking at different heights. Is there like a next step that you were thinking about there?
This was like the big main step we were thinking about because this regime change we believe is very interesting with the jet breakup.
I'm sure we'll stop there since we are at the time limit. So for the opponent, you now have 1 minute for concluding remarks. Z, you can start the timer immediately.
Yeah, so I think we've had a wonderful discussion. We've discussed many things, from the motion of the release mechanism at different heights, including at more extreme heights, the Navier-Stokes solution or the Navier-Stokes simulation, and its sort of shortcomings in some regards. The relationship between the qualitative explanation and the qualitative proportionalities to some more quantitative results. We talked about how varying the different parameters might affect the results in ways that were present in theory, but were not so much confirmed in practice. And we briefly touched upon jet formation regimes and the boundary conditions, and how we could possibly characterize those in the future. And we'd like to thank the reporter for this lovely discussion.
Sure, since we're done a bit early, we can move on directly to the questions from the reviewer. So you can move the clock forwards. Thank you. So reviewer, you have 3 minutes to ask questions of both the reporter and the opponent.
Yes. So I guess I'll start. My first question will be to the opponent. And did you consider the sources of the loss on the velocity? And following that up, do you think the sources of loss are important to the velocity of the jet and how tall it travels? So like turbulence or surface tension for that matter.
Like by loss in, so can you, oh, by loss in velocity, are you referring to like literally like drag forces?
Yeah.
I mean, I think it's not unreasonable to say, at least for the short drop heights that were present in the experiment, that there's negligible losses to air resistance. And loss to water is not really a concept that really makes sense in this context, because the loss to the water is the whole phenomenon, right? Because you're transferring this loss of energy into the jet. So
Okay.
it doesn't
Yeah.
really make much sense to
All
me
right.
to,
Yeah.
yeah.
And then the porter, why do you assume the ring had a constant velocity for the simulation? Or was that just some sort of restraint that was unable to be like changed in that case?
So this was like for the, well, we assume that the ring will reach a terminal velocity relatively quickly after entering the water. And this was then just basically simplified for the like visualization of the numerical simulation, therefore.
Okay, and then I believe if you can share your slides on one of them, you showed a times 50 slowed and 100 slowed and 110 slowed. Like you had three images.
Yes.
And I think, yeah, and those were played, and I think on the 50x slower one, the water jet hit the rod. And like, did that happen during your experiments as well? Or in that case, how did you stop the rod from hitting the water?
Yes, so I mentioned in the beginning we moved the 3D printer head away before the jet hits the ring. This was just basically shown for the first few milliseconds of the jet formation, just to sort of show the proportionality. We usually, of course, move the 3D printer head away from the jet. We always accounted for this by moving the 3D printer head away. It was just done specifically for this experiment without this because it would have been would have been too short of a time span.
Okay, yeah. Oh yeah, and then another one was the droplet formation. And how did you
What about the droplet formation? It'll happen due to the Rayleigh plateau instability, which happens with very thin water jets.
Okay, yeah, that was just my lead question about the droplet formation. So
you are out of time, so you can move on to the next phase. The reviewer will now prepare for their presentation. So the reviewer, you have 2 minutes to prepare your slide deck. So a quick time warning to the reviewer, you have 30 seconds left before you must present. Please prepare to share your slide deck. All right, see, so time's up. So can you start the timer for the next phase? Here, the reviewer will review the discussion.
Okay, so this is Problem Math Ring Fountain. I'm Luke, and I will be the reviewer. So, for mentioned before, we already know the problem statement, so I'm not going to say it. But these are the sort of tasks that we came up with. So, firstly was the experimental setup. I think the reporter did a very good job with this. Secondly was the source of the jet. I think they also had a correct identification for how the source of the jet was made. Thirdly was the characterization of the loss, and I think they didn't really discuss that, so it seemed a little unclear to me. And lastly was the parameters of jet, and they did indeed discuss all of them. However, I think there was a little bit they didn't discuss enough about the height, which was the most important parameter of the jet in this case. So this is a summary of the report, and for the theoretical analysis, they started with the Navier-Stokes and the continuity. They showed a fluid simulation, and they discussed the velocity and the volume. For the experimental confirmation, they started with their experimental setup, and then discussing the impact velocity. So these are the sort of merits that I think that were good done by the reporter. They had a very good experimental setup. They had an electromagnet and a flat drop. They had a good qualitative explanation and a variable declaration. So for the ring in the water, they had identification of regime change between the Worthington and Annulus jets. However, I still think there are some possible next steps. I think it would have been better if they had more explanation for the theory. For example, how the Navier-Stokes and continuity were used. They didn't really consider the source of loss and the change in velocity, which I still think could play a role in there. And they didn't really have any quantitative data. They didn't really have any graphs and visual data, even though they showed their simulation. And I think they could have gone more into characterizing the droplet formulation. So moving on to the summary of the opposition, some of their key insights were the simulation and how different parts were affecting it, the experimental setup and its flaws by changing a material or thickness for the rings, the multiple regimes and how much emphasis was placed on each one, and the drop from extreme heights. So I think they had some good merits. So they had a good identification of the reporter's points really well. So like for example, they identified Navier-Stokes, continuity, so on and so forth. They correctly pointed out there was a little bit of a intense focus on the second jet, even though the first jet should be higher in basically all cases. And they had a good questioning of the experimental result. There was no graphs, no error bars, even if there was a simulation. However, I think they could have focused on the source of loss, as again, the importance of the velocity compared to the jet. So I think these are some discussion points that were made. So, for example, the opponent raised the point with the would it affect the ring height? And they said it would affect the ring height with the thickness of the ring, but not by seconds per pound. I think I agree with the reporter here. The thickness of the coin will not affect the amount of water it displaces in reality, and the only way it could slightly affect it is if there's a faster velocity as the coin falls through water. Secondly, I think they had a discussion point on the focus on the first jet versus the second jet. The point raised by the opponent was how they focused on the second jet was not really part of the problem statement since they only cared about height. The reporter did agree with the opponent in this case, and of course, I'll agree with both of them here. And I think the first jet is important to the max height of the jet, not really the second one. Another one was the change in material. So how different materials would change the density and thickness of the rings. The reporter's response, I think, was fine. Although they didn't investigate it, they discussed that the main phenomena was the impact velocity. In this case, I would agree with the reporter. The ring material would change the mass and in turn change the velocity due to the reduced or increased drag coefficient, but I think that's quite minimal. And then lastly, I think they discussed a change in the velocity of the jet and how velocity could change over time. Reporter said this was a theoretical possibility and a proportionality is made between them. I agree with the opponent in this case. I think there are significant losses that would change the velocity over
You're
time.
over time now, so let's cut off. So let's move on to the next phase, C. In this phase, the opponent will now summarize the discussion and report.
The reporter or the opponent?
Oh, sorry, the reporter, yes.
Yeah, okay. So to summarize, in the discussion we talked first about like the mainly about the relevance of looking. Well, one of the main points was the relevance of looking at both jets. This is also something brought up by the reporter, and I'd like to the reviewer. Sorry, and I'd like to just clarify this point. We look at primarily the first jet because this is the jet which reaches the higher height. However, in the model, we model both jets as the task does not state if we should observe only the first jet or only the second jet. So we believe a more applicable simulation here is appropriate, as we can then observe more edge cases in the future, say with experiments. We then talked about, so with the discussion, we talked about measurements, for example, finding a sufficient relationship between the height and velocity, agreeing on this point. We then talked about the parameters of the ring, say the density, and we basically, in this case, we agree that the velocity is responsible mainly for the first jet, and since the second jet is affected more by mass and is lower, this is not as relevant. We talked about some boundaries of the experiment, say extreme drop heights with ring tilt, and talked about other relevant parameters, but we focus mainly on the velocity because of our experimental justification we showed. Now, going on to the review, the review did talk about the experimental setup being, for example, sufficient. We of course agree, and all parameters being discussed, like for example the height, but not thoroughly enough. We believe the ring height is proportional to the velocity of the jet, so we believe we have, in this case at least, sufficiently fulfilled this area. And also we talked about there was a point brought up about the usage of graphs instead of simulations. We believe a visualization using videos as well as simulations is more intuitive. However, a visualization with graphs could be done in the future for better overview. Thank you for your attention.
Your time's over, so now we'll move on to the juror questions. Jurors, you can start asking questions immediately.
I have one question for the reporter. In one of the slide I saw, it was like a very close-up picture of the disc falling on the water, and there was a slight slope over there. So my question is, how does the slope of the coin when it is falling down, not the coin, but like the disc, when it is falling down?
Okay, so if the coin is angled, one of the sides of the coin will hit the water slightly sooner, like we're talking about milliseconds or even fractions of a millisecond in our case, which means that the assumption that the coin hits the surface flat is not as valid, and the jet gets propelled slightly to the side since the radial momentum does not cancel out, since we don't have a circular shape, but rather a slightly oval shape at impact if observing from above. So the jet, which is propelled, will be slightly curved. However, we have observed experimentally this is within a amount of 3 to 5 degrees at most, so usually even less. And even at 5 degrees, the loss in the maximum height would be less than 0.4%.
Okay. And did you quantify the error in your experiment?
Sorry, the error or?
Yeah, error.
From the angle, as I've said, like the angle
From
will
various
be
factors.
from various factors.
Yeah.
Well, I guess we'll have like parallax error. We will account for parallax error, say from using our camera far away. I guess that would be like one of the main sources of error, which could be addressed here. But then again, also for the tilt of the coin, we usually take experiments with the most, with like the flattest impact. But even if they are slightly curved, the result should not be as big. These are the main two sources of error we accounted for.
Cool. Thank you.
Okay, I'll like to ask the reporter for your dimensionless numbers. One of them was Reynolds. Did you have a back of envelope numerical value? Like, was it 1,000, 10,000?
The value of the Reynolds number was around 24,000, which means that if we would apply this in our one-dimensionless Navier-Stokes equation, the viscosity term would approach zero because we have 1 over the Reynolds number. So this will be almost negligible.
Okay. Now, with your Reynolds number of 24,000, that's still around the transition between free molecular and continuum flow, right?
Yes.
And your simulation, was it you coded the simulation yourself or used the free software or?
We used a numerical simulation tool, Basilisk,
Okay.
for fluid simulations.
Okay. Are you have you used Basilisk? Like, is there a way to modify it to make sure that it does the calculations for a transition regime? Because Basilisk is much more used for something that's continuum flow, right?
Yes, I'm not as versed in Basilisk to I'm not sure in this case now.
Okay, no problem. Like doing things in transition is very hard. And last question, did you ever try dropping a ring where the hole was so small that you did not get a jet?
So this would be like if we had if the surface tension is like extremely strong or like capillary forces. We have not tried this, no.
Okay.
Because then we would only have only the corona and the air cavity.
Right. I mean, like, if you had the ring and the hole was needle sized.
Yeah. So it would effectively just be like a coin then.
Yes.
We have not tried this.
Okay.
Also, it's experimentally difficult to do this because we need to stabilize the coin around a rod, which if it's needle sized, we can't really do.
Okay.
Like practically.
Okay. All right. Who else wants to ask?
I'll go because it's kind of an extension of that question.
Cool.
If that's okay. So just earlier you had said that in the limit that the hole goes to zero and the mass, increases, the jet will become higher. And whereas now you're saying that, for a pinhole in a coin, you might not get a jet. I'm just wondering if you can clarify those two statements.
It's like we are basically observing if we are observing a limit towards where the ratio between the inner and outer jet is like approaching where the inner jet is very small. We are approaching like the so-called Worthington jet, like where the theoretical like perfect prediction. The problem here is though that if we have such a small jet, the capillary forces will be too strong that a jet would practically speaking not be able to form. So like we do have a limit in this regard as well. I guess I didn't clarify this enough in the previous phases.
No worries. Thank you. Thank you for
Can
the
we get
clarification.
one more Jira question, maybe? So either from Akash, maybe? Since you have your hand up.
Sure. My question is to Alan. In one of the slides, you mentioned that the second jet does reach heights greater than the first in extreme cases in theory. Do you want to tell what those cases are?
Okay, so we believe there is one main case where it could theoretically reach a higher height of the first jet, and this would mainly be caused not by like increasing the. We have to first of all we have to like theoretically verify this, but we believe this is not caused by increasing the strength of the second jet, but rather by decreasing the first jet so much. And the argumentation we would follow is like if we have a very large inner radius, the water, which is formed on the inside, will no longer concentrate as strongly in a point and will also form an inside corona. Now, if we keep the distance between the inner and the outer radius constant and slowly increase the coin, we would slowly weaken the effect of the first jet because we are dispersing the concentration more. However, the cavity formation would have a growing volume. So then the second jet could, in theory, maybe reach higher heights.
Sure. Let's finish up here. Sorry to Abhinav. I think you had your hand up. Since you're a bit over time and to be fair to the other teams, I guess. Sure. So now that this is finished, all of the jurors, can you please upload your score sheets to the drive? And this time we are only expecting 9 score sheets. So, and good job to the reporter, opponent, and the viewer.
It's the same folder, right?
Yeah, it appears to be the same folder. There's only one folder
Okay, great. Just making sure.
for the finals. All of you are so nice. I mean, the contestants.
Sure. Well, let's check how this is going this time. Okay, we have 6 out of 9 ready. Seems that we are progressing faster.
Louis, who's teaching you? Who taught you for Math 194?
Stainsby, so.
Oh, he's still teaching. My God.
Although he did die earlier this semester, unfortunately.
Oh my God. How about Civ 102?
It's different now. It's different
Civ
from yours.
102? Yes, I think that should be different. We're doing a bridge project. I'm not sure. Back in your day, did you guys do a bridge like at Howard?
Yes, with too much contact cement and some people got high.
Oh,
Right. Every year it's like that.
now I have Evan bands, but I know back in your time is different.
In which department?
Engineering.
Engineering, okay.
This is the Enshai lore.
And then
Yeah,
who's
that's-
teaching you Math 195 right now?
It's
Davis.
Yes, Davis.
Yes, ask Davis about a person named Neil Young. Let's see what.
Oh,
Yes, both in aerospace, right? Crazy.
Yes, yes.
You are a superstar at the University of Toronto.
Mhm.
Neil, you are a superstar inside the engineering department.
Ah.
All right, sure. We
Oh,
actually
like,
have
we
online
have
score sheets.
everything.
Yeah. Good job,
I remember
Travis.
Davis. Wait, Lou, have Davis
Yeah.
told you about Adam yet?
Yes. The failed nuclear physicist who
The
became a
nuclear.
success.
Fantastic. All right.
The generational stories. Okay. Sure.
Wait, the files are gone. Wait, where are they?
No, did someone delete all the files? No.
Someone deleted all the files.
Jeffrey,
Oh,
they're in day
I'm putting
2.
stage 2. Yeah, so I'm putting all in stage 2. Okay. That makes sense.
Sure.
Cool.
Now let's move on to the last problem of today. This will be magnetic cradle presented by Shumskis. The opposition for this problem will be Team Excel, and the review will be Team Germany. Since we can start immediately, we have all the jurors ready. So you can start the preparation for the reporter. The reporter will have 5 minutes to prepare for the problem.
The Team Shroomskis, there is no added points for nicely drawn images of dinosaurs skiing down.
Aw, that's sad. Are there any extra points for Germany's beautiful CaYPT logo?
Huh?
Are there any?
Did you see that logo? Maybe
Oh.
Germany
Did
can
you see it?
show that afterwards again. Germany had a very sketchy CYPT logo. I wonder if Team Maple Syrup can draw a maple flag. I think even Canadians suffer of this. Elaine, if you're ready to present, I guess you can get ahead.
No, I'm not ready.
Sure. Take your full 5 minutes.
Thank you. Okay, I am ready to present. Can you hear me?
Yes. If you cannot hear you, C, can you then, in this case, rest the timer and then start when the link starts talking?
Okay. Okay, hi, I'm Elaine Lee from Team Shripskis, and I will be reporting problem 11, magnetic cradle. This is CaYPT ordering. So the problem statement goes as follows. Repulsing non-touching magnets are used instead of colliding balls to make a new type of Newton's cradle. The new cradle can act in a similar way to a regular cradle, but can also exhibit other interesting behavior. Explain and study the movement of this magnetic cradle. Hello? Just lagging. So, some relevant parameters of this problem are the strength of the magnets, the relevant relative positioning of their placed, the number of magnets, the weight of magnets, and some possible things to take into account are the dampening, frequency, coupling, and the patterns that we can predict. So as an overview, I will first give an introduction, then I will explain my experimental setup, as well as an analysis of different type of motions, as well as a conclusion. So first of all, we model the permanent magnet we use as a solenoidal surface current, which allows us to compute the magnetic field as follows. And using this model and the Biot-Savart law, we can calculate the magnetic field produced by a finite cylindrical magnet at its displacement vector r as follows. And if we simulate this numerically using NumPy and Numba, the magnetic field at displacement vectors between magnets are tracked dynamically, and we can get near compiled performance. And due to computation time, our accuracy target is around here, so we will be using around like 250 discretizations. And this will give us a fast numerical solution of the magnet's B field. So as to why we're using this model instead of the standard magnet dipole model, we see that in the standard dipole model approximation, the B field would be obtained as follows. However, although the dipole model does agree with the cylinder model at large distances, it breaks down at small separations. And in our case, our magnets, while simulating the magnetic cradle, we would think the current cylinder would be better. Then the magnetic force on neighboring magnets is computed using the Lorentz force law, and we would work in the reference frame of one magnet. Combining magnetic forces, gravity, tension, and damping, we derive the full equation of motion for each magnet, and then we use the parallel axis theorem to account for rotational inertia, and this results in a couple nonlinear system of differential equations. And solving this ODE with RK4, we can build a numerical simulation with the following assumptions and computational tricks. So for our experimental setup, we have a wooden board drilled with 1 cm apart drilled holes, and we extend rigid wires through the holes that are around 9 centimeters in length and hang the magnets as such. Here is a labeled picture of our experimental setup. And we use a DSLR camera to track the movement of the magnets and then process it through tracker. And all objects are on the same image plane. And here is another label picture. So we characterize our magnets using a lab jack and a Tesla meter setup. And here are the magnet dipole moments and magnetization of each of the magnets. We use identical magnets, 0.636 cm in radius and around 0.63 cm in height or thickness. So for areas of study, we will first explore the 2-magnet case using a simple coupled oscillator model, and then the 3-magnet case, as well as further insights into many different magnets. So our 2-magnet system can be thought of as a simple coupled oscillator like this one on the right. Each magnet will feel a restoring force from gravity, which is associated with a natural frequency of omega c, and the magnet force can be thought of as a spring squished between both of these forces, which is also associated with like a natural frequency of omega b. The magnetic force expression that we previously obtained from the slides can be written in terms of individual displacements of the magnets x1 and x2 as shown. And by making a binomial approximation, this can be rewritten as the following, which is some constant minus another constant times the difference between the two displacements. This setup where the force is proportional to the displacement gives an expression for the frequency. And now we have this magnetic force associated with a frequency, and we can also have a restoring force, which is associated with another natural frequency. The magnetic force and the restoring force act in directions as shown in the diagram, and by rewriting Newton's second law, we can rearrange to get the following two expressions. From those previous two expressions, we can add both to obtain the equation for symmetric modes and subtract them to obtain the equation for anti-symmetric modes. Our simulation modes look like both springs. Our symmetric mode looks like both springs oscillating in phase at the same frequency, like this one. The anti-symmetric mode is the case where both strings oscillate out of phase at the same frequency, which this explains why we observe 2 beats in our FFT. And the motion of the magnets is produced by basically the superposition of both of the two modes to produce a quasi-periodic motion. There are some issues to our analytical solution, and we will observe the deviations from experimental results later. The analytical solution provides qualitative insight into existence of modes and their different frequencies. However, magnetic force is highly nonlinear, and it is not right to model. It is inaccurate to model it with a spring, and as you can see. So in our actual simulation, we use a numerical simulation for comparison, and we use analytical only for qualitative understanding. We see there is a beat frequency in our data, which implies 2 frequencies. This is the resonant frequencies of 2 modes. When superimposed, they create a beat frequency. To analyze this, we perform a Fourier analysis to transform the signal into the frequency domain. And here are some plots data, and we also produce a simulation copy of our data for experimental theory verification. And we perform peak detection to extract mode frequencies. And the reason we do this is because how dominant a mode is dependent on initial conditions. Thus, we only analyze the mode frequencies instead of the full path. And doing an FFT from the previous motion time equation, we observe 2 distinct peaks which correspond to our symmetric and anti-symmetric mode. We see that the symmetric mode lines up really nicely with our theory, while our anti-symmetric mode doesn't quite line up due to probably most likely deficiencies in the magnetic model. And for qualitative explanation, as for varying length or like separation between the magnets, as the separation approaches infinity or like infinitely greater than the length of the string, the coupling of the magnetic forces approaches 0. So the system simply becomes 2 simple pendulums, and the FFT would the peaks would get closer and closer, so that until they only produce 1 peak. And as for the 3 magnet case, here is a GIF of our simulated results. Here is our experimental data, and we can observe from our FFT there are 3 distinguishable frequency peaks. And we see that the magnet 2 is the yellow one, which is the center magnet. It only has 2 modes. This is qualitatively explained because, as you can see from the experiment, even though these are slightly out of sync, the frequency is correct, and it only has 2 beat frequencies clearly visible. And our data and theory frequency map lines up pretty well. And as for further insights into many magnets, we don't really have experimental data on this since we only had access to 3 magnets. However, as we see, as we approach infinitely many magnets, the motion becomes increasingly chaotic, and we can analyze this using Lyapunov's exponent. Basically, this quantifies how fast two similar trajectories diverge by taking the distance in phase space over time for two close trajectories. We can fit an exponential, which a positive exponential indicates the trajectories would diverge exponentially, which would indicate a chaotic system. And we iterate it through many close space values to find an accurate average exponent. And as we see, a positive Lyapunov's exponent is shown, indicating there is chaos within the system. And with more time, we would love to investigate emergent stable modes, but for now, as a summary, first we took a qualitative account of the system. We modeled the magnetic B field and force at a given displacement vector, and then we derived the ODE for the magnet motion and built a simulation using RK4. Then we built a numerical model and we built an analytical model of the coupled oscillator for two magnet cases, and we had a numerical solution for a frequency / path of symmetric and anti-symmetric modes. And we had a numerical simulation of 2, 3, and many magnet cases, and we also showed experimental theory frequency mode matches for 2, 3 magnet cases. And then we did an analysis on Lyapunov's exponent and chaos for many magnets case. And here are references. And thank you so much for listening.
All right, so we are done a bit early, but we move on directly to the opponent questions. So would the opponent please come up, and you have 2 minutes for rapid fire questions.
Okay, the first question I have is, how exactly did you displace your magnets in your experiment?
For the displacement of the magnets, we displaced it by hand. Unfortunately, we did not build a release mechanism, and we did use a protractor to measure an angle. However, as we've stated before, due to the displacement, the initial displacement of the magnet having a large impact on the path of the magnet, we chose not to actually analyze the path of the magnet, instead taking an FFT to analyze the frequency of the oscillations. So even though we displaced it by hand and there could have been inaccuracies, we don't think this had a large contribution to our theory and would not cause any
Yeah,
deviation.
that's okay. Moving on to my next question was, did you experiment using different magnets like size, types, or shapes?
Unfortunately, we did not experiment using size, types, of shapes. However, we did build an incredibly accurate simulation for the path of the magnet. So I would think if we use different size, types, of shapes of magnets, it would, like for example, with different B fields, it would match really nicely with our simulations. However, that is to be explored.
Okay, yeah, that's also needed. Another question was, since you used this simulations, what were the parameters set inside of your simulations?
The parameters were set to the experimental data we gathered, which is if we go back. For our experimental trials, we did for 2 magnet and 3 magnet cases. As we've stated before, we used identical magnets of 0.63 centimeters in radius and 0.63 centimeters in height and thickness, a wire length of 9 cm, and then we had varied magnet separations of from 5 centimeters to 10 centimeters. Those are the parameters within our simulation.
Yeah, that's it. I don't think we have enough time for
Yes,
any
the
other
rapid fire
questions.
is actually over, so we'll move on now to the preparation of the opponent. The opponent, you have time to prepare your presentation. You can start now. Great. So a quick time warning to the opponent. You have 40 more seconds to share your slide deck and begin the presentation. To the opponent, you're over time now. So please ensure that you're sharing your presentation right now. Otherwise, we'll start the clock.
Yeah, okay. I'll share.
Okay, Z, can you start the clock now?
Okay, so this is question J, the magnetic Newton's cradle, presented opposition to Team Excel. So this is the problem statement. So the problem statement is repulsing magnets are used instead of colliding balls to make a new type of Newton's cradle. The new cradle can act in a similar way to a regular cradle, but can also exhibit other interesting behavior. Explain and study the movement of this cradle. So the four tasks that were determined were: first was to observe and describe the motion of the magnetic Newton's cradle, and what are the similarities and differences compared to a normal Newton's cradle. Two are identify and the varying key parameters. Three is to model the interaction, and four is to analyze the energy and momentum transfer. So this is just the summary of the reporter. So first we have B-field simulator and the cylinder model. Two was the equation of motion through the Lorentz force and the number of magnets. And three was the experimental setup and verification. And it was shown in visual data like graphs. And it showed a strong correlation between the theoretical and experimental data. So these are the merits and next steps. So for the merits, there's a clear characterization for the magnetic force and cylinder model. Two are the animations and also the explanation of different modes. And three are the frequency peaks. And four is the investigation of physical parameters and how they affect the motion of the magnet. Possible next steps could be the release conditions. So maybe try using a non-magnetic stand instead of using a hand, as it would be more consistent. Two would be more variation. So you could test variables such as shape, size, and type. And three is just setup. I'm pretty sure I saw on your image on the first slide that the wires were bent in my hand and not perfectly straight. And this could possibly alter the results. And just the overall questions asked here. So first one was the displacement method of magnets. You stated that it was used by your hand. Two, are the different types of magnet used? You said that you didn't get enough time to test it. And three was just the simulation parameters. You stated that it was the same parameters that you used in your experiment. And that's it.
Sure, wonderful. We can move right on to the discussion then. Z, can you progress the timer to the discussion, and reporter and opponent take the stage? Oh, are you guys? Yeah, please.
Yeah. My first one is for your Lorentz force. I'm pretty sure it assumes that that the magnetization is uniform, but in reality it is not for permanent magnets. And is there like another theory you could use instead of this one?
I think the reporter is muted, by the way.
Yeah, Elaine, you are, no sounds.
Oops, sorry about that. Yeah, you would be right. For Lorentz force, I do assume the magnetic field is uniform. However, wait, it does also account for some deviations within the theory as shown in one of the slides. I think, however, the deviations aren't since there is a really good like theory experimental match for the frequency, I think these effects aren't really like that significant, and Lorentz force model is sufficient. However, if you were to model the actual path of the cradle, I think it would probably be good to use another model, a non-uniform magnetic field model that could possibly better like simulate the problem.
Okay, another question I have is, did you treat your magnets as ideal point dipoles?
Yes.
Okay. Another question I have is, you use the Biot's Sauert's law, which applies to, pretty sure it applies to electric currents.
Sorry. Hold on. Sorry about this.
Yeah. So for that law, your magnets don't have electric currents. Is there another theory or theoretical model that you could use?
Wait, can you repeat that question? You were a bit quiet.
Oh, so you use the Biot's Sauert's law, which applies to electric currents.
Yep.
And I was wondering if there's like an equivalent model that you could use for magnets that don't have an electric current.
Um, hold on. Wait. Let me wait, hold on. My slides are lagging on my side. Wait, can you see the Biot-Savart law slide?
Yes, I can see it.
Yes, okay. Yes, there are definitely other models I could have used. However, as I said, I think as there is a really good experimental theory match, I think this model is sufficient. I in literature, of course, I did explore other models, and however, I also according to the B-field simulations I have built, I think this is sufficient
Okay, and you
and a
say
good
that you didn't,
characterization.
yeah, and you say that you didn't have enough time or the resources to test size, shape,
Mhm.
and types. Can you tell me what your prediction was if the size were to change or the shape?
For the size and shape of the magnet, of course it would just the largest effect would of course be the magnetic field. If there is an increased magnetic field, of course there's going to be more energy and more force upon the pendulum, so there's going to be perhaps faster frequencies. I would think that since where there is no contact within the actual pendulums, the variation of shapes of the magnet would just lead to like the only possible difference that would make is if it produces a non-uniform magnetic field. In that case, we would probably use different models for non-uniform magnetic fields to better model the path of the magnets and the forces experienced by the other magnets. As for other parameters, for example, like the length of the wire maybe, and like as if you like increase the length of the wire, there would like basically the length increasing the length of the wire, like it's at a ratio between like the distance between the two the separation between the two magnets, right? So if you consider the ratio between the length of the wire and the separation between the two magnets, I think this will be it'll be like around the same no matter like how long the wire you use. Maybe there will be slightly less torque and dissipation. Yeah.
Yeah. Another question here is on your introduction slide, you had sorry, on one of your tracker slides, you had an image showing like a video or an
Yes,
image
I know
of
where
your
that.
setup. Um, and in there I saw wires were physically bent. Um, wouldn't it be more consistent if you had like wires that were fixed and you could just put magnets on, as there could be like human error to this one? Like to the wires,
As
as
in,
if like the magnets were like angled differently and not perfectly straight.
wait, yes, the bent wires are they definitely have an effect. However, I would think that because I think the wires are rigid enough such that they would not like physically bend in the process of vibrating in the magnetic cradle. However, it would definitely be better to use perhaps like a more linear or rigid wire for just better tracking and I guess more accurate experimental results. However, I think the torque displacement would it wouldn't have a large effect on like the actual like frequency of the vibrations or like the torque displacement. It would definitely have be like perhaps a shift to the initial like displacement, like it would there would be effects to the tracking definitely.
Um, Another question. Um, how exactly did you accurately measure when first coupling happens?
I'm sorry? Wait, I couldn't hear your last three words.
Did you measure? Okay, so you mentioned coupling in
Oh,
prior
yes.
slideshow. Can you tell me how you accurate, like, what was the process to accurately measure this? Like when the first coupling happens?
What do you mean? Like the coupling between the
Yeah.
magnets?
Yeah.
Yes. I actually I did not actually like measure like the like a boundary where like the coupling starts from like for example the initial position. However, like as I have said, I have took my experimental data and I have used an FFT, so I actually do not have like a boundary for like when like for the path of the magnet when the coupling actually starts. However, I think based on the frequency graph, we can see that there is definitely coupling happening, and I think that is sufficient for my analysis. As I have
Okay.
said, because due to like the instability of the magnetic Kratos initial release conditions, as it would be difficult for me to model the actual path of the magnet, therefore I have resorted to using an FFT and that Fourier transformation analysis.
Okay. Because you were unable to have enough resources to obtain more than 3 magnets, what are your predictions on what would happen if the number of magnets would increase?
If there are more magnets, I would think there would be because there would be like more modes of the like as we have seen for the 3 magnet case, there are already 3 modes, and due to the different coupling effects of adjacent magnets, there will be increased amount of modes for more magnets. And so for the FFT graph, you would observe more peaks. And of course, as magnets increases, a small perturbation would lead to a larger deviation between the two. So basically, there would possibly be like chaotic effects if there are tiny perturbations,
Yeah,
perhaps
okay.
due to air resistance.
Another question I have is, does any of your models include magnetic torque? I'm not sure if I saw one.
Yes, I'm pretty sure magnetic torque is included. I'm pretty sure it's just included in my original ODE.
Oh, okay.
Yeah.
Okay. Another question I have is, um, when you determine experimentally, because you like displaced it by the angle, what was the minimum amount of angle? Like what was the smallest angle you get to before the cradle would sorry, what would the minimum angle be before the cradle wouldn't achieve coupling?
Again, we did not necessarily investigate the exact moment when coupling starts or when or like the actual path of the magnet until it gets to coupling. However, because we took the data over quite a long period of time, so I don't think the initial motion of the magnet before coupling contributed to a large part of like our FFT and had implications on the frequency graph. However, I would assume that if we were to analyze when the initial coupling starts, it would probably be a few revolutions. I do not have an idea. But it would be certainly interesting to investigate.
Okay. Pretty sure that's all the questions I have.
All right, Chip. In this case, then we'll move on directly to the preparation of the opponent. For the opponent, you have time to prepare your presentation. Wait, sorry, is this... Did I skip it? Sorry, this is the concluding remarks of the opponent, I believe.
Yes. Okay, after a detailed discussion, multiple clarifications were made, like for example, the reasons to why they chose the models they use compared to other theories, as well as reasons to why they assumed, like for example, the dipoles, as well as a clarification on like the things they test. As they stated, they were unable to test the different magnets in terms of size, types, and shapes, as well as the number of magnets due to time constraints, as well as like a limitation of resources. They also clarified on how they displaced their magnets, which they stated by hand. And a couple of suggestions that I made are maybe you could use a stand, a non-magnetic stand instead of a hand, which for more accurate results, test more variations like size, shape, and type, as well as there might like use a more consistent way instead of bending the wires to reduce the amount of human error.
Is Luyu here? I
Sorry.
think its Wi-Fi got glitched.
Yes, I believe that the stream is having some issues. Can you guys hear me? Or
Yes, I can hear you.
oh, okay. Oh, the stream. Okay, it's back on now. Okay. Sure.
Yeah, see, let's move on
Yes.
to the next one.
Let's move on to the next phase. This will be the questions from the reviewer to both the opponent and the reporter.
I will be the reviewer for this match. My first question is, you meant to the reporter and opposition, you mentioned you had a good match between the simulation theory. Do you have any plots showing us the simulated force between the magnet and the actual force between the magnets?
I do not have a graph showing
Okay.
measuring force of the magnet.
Thank you. Now to the opposition, how is it then believable that the model they used is appropriate and actually models this correctly?
Yeah, so for the assumptions they made was they assumed sorry. Then they assumed that there was uniform distribution for one of them I asked. They made this assumption as the formula they used was the Biot-Savitz's law. And
Thank you for
then
elaborating, but I was just like wondering, just a quick yes or no, and because I don't think this is actually like enough to show that the model is appropriate. Now we are talking about the release. Is there any way to make the release more reproducible?
For more reproducible, for example, we could perhaps take a stand, or we could perhaps like use like a string, or build like some kind of release clamp.
Okay,
Wait,
thank you.
also I would
I
like
don't
to
want to interrupt, but we have to go a bit quicker to like get all the questions done. Now, assuming you would have that more better release, are there any other sources of error in your experimental setup that would not allow you to compare the theory simulated motion to the actual experimental motion?
there is varying there is a
Just
lot of
quickly, if there are yes or no, just like quickly.
yes, there are many
Okay,
different
perfect.
errors. Yes.
Now I want to come to you mentioning chaos. Can you shortly again explain us very quickly how you calculate the Lipinov exponent? And explain what the number actually means for your experiment?
Yes. Let me just go to the
Just
slide.
give us a quick intuition what the number 180 means.
Yeah, the number 180 means because there's a positive Limesnoff's exponent, that means there could be chaos that's in the system.
No, specifically the number 180. What does it mean? So,
It's
for
just
example,
the convergence of basically like this will take more time to explain. I don't think I can do this in 6 seconds.
I can understand. Okay, thank you both very much.
I'm sorry, my Wi-Fi did actually cut out for a second, but we're out of time for this phase. Let's now move on to the next phase. The reviewer will now prepare their presentation.
Can you see my screen?
Yes, the screen is visible and you have 10 more seconds. So you can start when you'd like.
Perfect. I will then start now. Hello, my name is Kurt. I'm presenting for Team Operation Ahornsirup, the review of the project Magnetic Neutral Cradle. I think we all are familiar with the task. Coming first to the reporter's job, they define the key parameters, and also we think that using BSABR for the magnetic molding is appropriate. Last, we also think that the variation of various modes of behavior are very interesting, dividing it into the 2, 3, and multiple magnets case. However, here we clearly miss the task where it asked us to investigate where we see parallels with the Newton's cradle, which wasn't really mentioned enough. And as the motion was also investigated, we couldn't really see that part of the task being fulfilled. Then also, the theory for the two pendulums was not clearly explained, and that was also why the opponent asked about the linearized model. And lastly, what was very important about the presentation was the Lyapunov coefficient, which we thought was very interesting to measure. However, it's usually around 0 to 3 and not around 180. 180 would mean that in the time frame of around one second, the deviations would increase by a factor of 180, which is not really applicable for the system, and which makes this calculation pretty questionable. And also, we think that the experimental setup wasn't sophisticated enough, as we saw some imperfections with the wires, but also with the release mechanism, which you think was way too inaccurate. Now, coming to the opponent's job, I think it was very good that they immediately recognized the errors from the wires in the setup, as they were seen in the video were not straight, and therefore caused errors in the experimental setup. And also, we think the errors from the hand release are very important, as this was one of the main points lacking in the experimental setup. And also, I think it's very important that they asked about the increase of magnets, as when you increase the magnets, you could maybe easier show the Newton's cradle of the transition of the momentum through the system. Then we believe that unfortunately there was some missing depth in the question regarding the magnet modeling. We didn't see enough challenging of actually seeing the implementation of this theory and seeing a direct comparison between the experiment and simulation. We think that would be very important. And also, we think there was some discussion of less important aspects, which we'll be talking in a second in the discussion. And finally, we think they should mention the task fulfillment as it asked for the movement and also the comparison to the Newton's cradle, which wasn't really done in this presentation. And also, we think there was a misdiscussion about the chaos. Now, I'll transition into the discussion. So first, the opponent asks if the Lorentz force is uniform and if another theory can be used. And the reporter answers that they assume that the magnetic field is uniform, and they also account for some deviations in the theory. And finally, they said that they don't agree as it agrees with the theory and with the experiment. However, in our opinion, even though we agree with the reporter that the theory and that we can use this model, we still think that the correlation between the working theory and experiments was a bit questionable, and that this argumentation is a bit circular. And then we had the opponent ask about the various sizes and shapes of the magnet, where the reporter answered that this can be modeled with Biot-Savart, and we agree that this is applicable for magnet modeling also for different sizes of magnets. Then the opponent asked when does the coupling start of the system, and then the answer was that no measurement of the time was taken, and we agree with the opponent that this time that it takes time for the coupling to start, and it's very important for the task fulfillment. And we also think that the motion of the cradle should be implemented. And finally, coming to the task, we think that it was only partially and even insufficiently fulfilled, as the main aspects were not addressed. Thank you very much.
All right, so you are finished now. Let's now move on to the reporter. So the reporter, you have 2 minutes to summarize your presentation, the discussion, and any additional points you have.
Okay, first of all, thank you, Team Ahunship and Team Axel for this amazing discussion. And I would just like to give a few clarifications. First of all, the magnetization in permanent magnets is actually effectively uniform, and I would like to highlight that the B field through the magnet is not uniform, as the magnet that's affecting it produces a non-uniform field, and we do in fact take this into account. And also, to Germany's statement on the verification of our magnetic force. This force is correct because we do characterize the magnetization of the magnet, and the force, since the force is really only dependent on the magnetization of the two other magnets and their geometry, the force model is fine. And also, for the release mechanism, it is important if we were to investigate the position time space. However, in this problem, we are more interested in just analyzing different modes of motion that can occur in the system, as we believe this aligns more with the problem statement of a Newton's cradle. Given more time, we would of course love to analyze, fully simulate, build a model of the path of the magnets through the position time space. And finally, on the chaos analysis and on Lyapunov exponent, for us, the Lyapunov exponent is in phase space, so it actually increases very fast. That's why it's such a large number, and it includes both the angle and angular velocity of each pendulum. So we will investigate Lyapunov's more given more time. It's currently there right now just to demonstrate that there is a positive exponent, therefore there is chaos given more magnets. And also, we would just like to conclude with saying this project was a team effort. We were really sorry for the confusion. Another team member did a lot of problem and couldn't make it today, but he had a bunch of clarifications. Thank you very much for the opposition and for the review. And we would like to invite the judges for some questions.
I'm sorry, I was using the wrong microphone. So yes, the time is now up, and now we will move on to the juror question stage. Jurors, you'll have 5 minutes to ask any questions. Please ask as you wish.
Perhaps I can start. I just had a very quick question for the reviewer. So at some point you mentioned measuring the force between magnets. Did you guys do that? And if so, how?
So I want to firstly clarify that the report did measure the magnetic moment and can compare between the theory and the experiment. However, what I want to focus in is when you rotate the magnets, then measuring the force. And how you can do it is using force sensors. However, you have to be careful to actually use sufficient distances to the force sensors to ensure that the force you measure is actually appropriate and doesn't come it doesn't influence the apparatus of the force sensor itself.
Sorry, could you clarify what exactly do you mean by force sensors? Is that something that makes contact with a magnet? Is it on the magnet itself?
No, so what I mean is you could use a force sensor and you have to be careful to not have it immediately at the magnet, as the magnet could influence its working. However, by spacing it apart, by using some material in between that like conveys the pushing like the force of the magnet onto the force sensor, you could then actually calculate that force.
Okay, thank you.
Thank you.
Just to clarify, for a reviewer, don't force sensors require, contact for you to register your electric potential difference? And this entire setup doesn't contact at all.
So I feel like I need to clarify this. I'm talking about if we first assume that there's some model that we use to for the magnet's force. I'm saying we should make an independent experiment where we take two magnets, rotate them by some degrees, and then measure the force, not directly by using the force sensor at the magnet, but by having a material in between that conveys the force of the magnet onto the force sensor.
Okay.
That's what I meant.
Okay. And earlier in your presentation, you had a split between either the reporter, I think you put task insufficiently fulfilled, and the other person task partially fulfilled. What is the difference between insufficiently and partially? Aren't they the same?
I mean, to be honest, the wording itself is not as, in the end, I just wanted to convey that I think the task of both was not fully fulfilled, and it was just like a different way of putting it. There's no qualitative like difference.
Okay.
Thank you.
Sure. Do any other tutors have some questions? Go ahead, Ahmed.
Yeah, I'll just ask a question. So this is for the reporter. Can you pull up the slides where you approximated the bias of it?
Yes, hold on. Let me pull up the slides first.
So you showed a slide where it says that approximation for the dipole is not relevant at small distances, right?
Yes. Somewhere around here. Here.
Okay, can I see it?
Yes.
Okay,
Wait,
do you
sorry.
experience that small of a distance in your experiment?
As in like between magnets? I would
Yes.
say even though the magnet never makes contact and also basic like for our experiment, I would say the distances between the magnets are often less than like 2 to 3 centimeters. So I think there is like in an effort to minimize like possible deviations from the magnetic force, we took this current cylinder model.
What was the strength of the magnet used in the experiment?
The trend of the magnet
The
used?
strength.
Oh, the strength. I have a characterization at some point. Here.
Okay, pretty small. Okay.
Yeah.
Okay, that's a reasonable assumption to make then.
Okay.
This is another question for the reviewer and I guess to the opponent. At what kind of like for your experiments, if you did it, did you use the bias savant or did you just use the dipole approximation?
So I tried both, and I had experienced that the dipole model does not work sufficiently enough for small differences. As we already talked about, there is chaos in the system. So for the small displacements between the magnets, we need to very accurately be able to predict how much force it generates, because otherwise, over time, we'll have larger and larger changes. So I do think the dipole model is not applicable, I think methods like Biosaba is here very good to use.
And the opponent?
Opponent, you're muted if you're trying to talk.
Wait, sorry, can you just quickly repeat the question?
So opponent, for your experiments, or like based on whatever you have done, would you use the biosavart or would you use the dipole approximation
I would
for
use
your
the dipole approximation for my experiment.
So we are out of time at 6 minutes. So to be fair to all the teams, we'll stop here. And so for the jurors, once again, can you upload your score sheets? That's the last time this year. So please upload them to the finals document in the drive. Thank you. Yes, and maybe Jim and Jeffrey, do you guys want to take over now?
There's
Yes,
no
just make
separate,
sure
there's
the
no separate
things are.
folder for stage 3 at the moment.
Just put it directly in the finals
Just
session.
put directly
It's
in
okay.
the place. We'll sort it out. Hey, fantastic. I think we are actually really ahead of schedule. It's 6:44 right now. This entire final supposedly should end at 7, but I guess we're super efficient and we get the thing done before 7.
I guess I've been rushing people too much, you know.
No, we are perfectly fine. So what's going to happen next is that the committee will start calculating the marks in the finals, and shortly, we don't even need a buffer time. We will let you guys know when the award ceremony will begin, and we will start distributing the medals and, of course, virtual medals, and the awards to the participants. Just wait here for a minute. Yeah, and it will be a chill time between now and 7 p.m. You may chat or you may do whatever.
Continue the stream. Don't stop the stream.
Oof.
I
Sorry.
heard you, Jim. Okay.
Continue
Yes.
the stream, by the way.
Yes,
Sorry,
I
Jim.
will
I
continue
was
the
having
stream.
the Discord voice on. Yes. So just this will be a chill time. You can chat. You can do whatever you want, and we'll calculate the mark and we'll let you know. So just come back at 7, and we'll see you back here.
Right.
I have to run, so I'm just going to say congratulations to all 3 teams, regardless of how well they do. But I have to go pick up someone at the airport, so
Sure,
good job,
definitely.
everyone. So see you next year.
Thank you, Matt. Thank you,
Thank
Matt.
you,
Oh, by the
guys.
way, Louis, check if Matt's like score sheet is here yet.
Matt, did you upload your score sheet?
One second, Matt.
I did.
Okay,
I did.
great.
All right, fantastic.
You
See
have
you
some
next year,
info
Matt.
me and yeah.
See ya.
See ya.
Don't worry, don't worry. Come on.
I trust you, Matt. All right. Okay, I think we can, let me check. Do we have the final mark out yet? Okay, the jurors are all leaving already. Wait, Jim. Oh, oops, I'm muted. My bad.
Still missing a score sheet, is that right?
Are we? 1, 2, 3, 4. We have 7 score sheets. We need 9. Oh,
This one
Oh,
better
yes,
not be Matt.
we
Yeah.
how many score sheets are we having? Still 7? Oh, oof, that's not good. Let's see if we have. Let me start logging the score sheet into the system and
Oh,
see.
got one more. 1, 2, 3, 4, 5, 6, 7, 8. I don't think we have one from Osama yet, right? Mohammed Osama.
Yeah, I'm uploading. It's just taking a second. If you
Okay.
want, I can
Cool.
maybe
Yeah,
pop something
it's
in the
okay.
chat.
We can wait for the upload.
What?
That's
Ooh.
Jeffrey, are you entering it into the spreadsheet?
Yes, I'm entering
Okay,
them.
cool. Got it.
Oh, this is so interesting.
Oops, I uploaded the wrong one. I uploaded the latest one now. Can you double check? It was stage 3.
Stage 3, okay.
All right. Yeah. Okay, I'll double check. Ooh.
Okay, I got it, yes.
Every time I say woo, people are like, oh, oof, something's going on. Oh. Okay. Are we having all the... I think we're still missing Mohammed.
Yeah, it's just Google Drive is just, I don't know. It's like a 1 MB file, but it's refusing. I can maybe put scores in the chat
Oh.
somewhere if you would like, or
Yeah,
email
just
them.
send it to the host who's running the Zoom call right now.
Yeah.
Okay, I'll just send it.
Yeah, that'd be
Thanks.
useful. I'll forward that one to them.
The scores are so interesting. Let me double check the scores before releasing them.
Don't tell me there's a tie.
Oh, there won't be. There won't be a tie. That I can guarantee. Oh. Wow. Okay.
Well, interesting.
Interesting.
Interesting. Okay.
Yeah,
I think we are doing well. We're doing very well. Good.
Let me double check the score. Let me double check. Just one
All right,
last check.
Jeffrey, I'm forwarding you the last juror right now.
Which
So
juror?
Mohammed, right? Who sent it via chat.
I think I already counted his into it.
Oh, okay. So it did upload.
Yeah, I think so.
Check.
Okay.
Whoa. Jim,
That's
can you
good.
double check the score as well? So in case I made a mistake somewhere.
I think it looks all right. Yeah.
Okay.
Yeah. I think that seems very reasonable.
Oh wait, one second. No. Mohammed score, I uploaded the wrong one. My bad. Yep. Now who was the score I just uploaded? Okay, I might have messed up. One sec. Mohammed. Let's see. Okay, here.
I'm not seeing the
Okay.
Yeah.
No, just let me do a final round of check.
Yeah.
I've uploaded something wrong, so here this was correct. Where is he? Okay, I see where I uploaded something wrong.
Don't tell me you divided by 0.
Nope.
No, we're
Otherwise the
okay.
Excel will
We're
crush.
okay.
The Excel will tell me I did something wrong. Reviewer marks is this? Okay. Correct. This one is, who is this? Oh, it's new score sheet.
What? What happened?
No. Just just checking. This one's great. And this one's great.
Yeah, our system is getting very marginally more robust every year.
Marginally robust
Marginally, yes.
by using
Yes.
manual system, like
No,
computer
no,
system,
as
and
in
then bigger brain
our like
manual.
management system. Yeah. It has
Okay,
gone
Jim, I
through
think
like
the score is
at least
correct.
3 generations of high school students to get this like developed and up and running. Yes.
Exactly.
Do you have
All right.
something that defeats me overriding the system? Not anymore, right?
I mean, as long as volunteers don't go in and go like, this problem is banned, but the system let me chooses it, so I will still
Right.
choose it.
That happened this year.
Yeah, that happens. Yes.
Oh no, this year there's a bug that you can do two same problems in the same round, and then the
Well,
bad
it
one.
does say that it's banned. To be clear, the
Yeah, it
system
does
is
say
not
it's
very clear.
banned, but the
Wait, no,
volunteers
it doesn't say it's banned. It doesn't say
It does, doesn't it?
No, it
Oh,
does.
okay.
It does.
Yeah,
It
does,
only
okay.
says it's banned unless the person has more than two problems to choose from.
Yes,
When you have less
yes.
than two problems to choose, you lift that ban.
Yeah, that's why like a 17 problem IYPT rule can't be mapped directly to a 5 problem CAYPT rule. That's when everything collapses. And
Exactly.
also we have this very elaborate sort of like medal scheme, right? 15%, 30%, 50%. But then when you only have 3 international teams, it kind of doesn't work. So we have to, like do what we see fit kind of thing. Yes. But I think as a first year within international teams, it's very fun. I like all the memes. The memes are great. Yes.
Let me
Yeah, the
see.
memes have been picking up a lot, I see. There's suddenly a lot of memes in the server.
Yeah, like while the final is going on, there are a lot of memes about it already.
And I think this year is uh it's probably the only year that we've actually finished early. The finals
Yes.
always drag on for very, very long.
Oh, because in the past, we would allow jurors to ask more questions.
Yes.
Yeah, this year you guys
Sure.
you cut it off. We're like, okay, fine.
And also we've sacrificed everyone's breaks because yes. Yeah, because I guess well for people in Europe is late at night. We don't want them to take a break. We just want to finish and let them go to sleep.
I wonder if the Hong Kong people can come for the morning now. It's nearly 8 a.m. So,
Right now?
yeah, it's about 8 a.m. right now.
Back in those years when we were doing OYPT, I was judging some of
Oh
them.
yeah, I remember.
And then
Yeah.
I went there and then I'm like started judging at midnight and then finished at like 6 a.m. And then it was during the summer, right? So I would like just go outside, like walk outside, take some fresh air, and then like pet the geese. So
Jim, I
yeah.
remember in 2022, that
Mhm.
year, like
Yeah.
when after we finished that day, you came here like, oh, I gave the lowest mark again.
Oh yes, yes, yes. I was, but I gradually calibrated myself, hopefully.
Oof.
Yes.
Jim, where are you working now?
I'm doing my PhD at U of T.
Ah, okay.
Yeah. Still, I mean, a bit more than a year to go.
Okay.
Yeah. Maybe a
Wait,
year
Jim,
and
Jim,
1.5 semesters. Yes? Uh-huh.
can you double check one thing? Is uh, can you double check the number of bronze and stuff?
Uh, check where?
After we updated the number of participants.
So which file am I supposed to look at? Like did you send a new like
Oh,
PowerPoint or something or?
yeah. I was about to send you the new
Oh,
one
sure,
here.
yeah.
1 second. Wait.
I don't know, like time flies. I feel like I like
You're old.
like yeah, like these few years of PhD went by pretty fast. Yeah.
I just sent that in the chat. You can check.
Yes, yes.
Yeah.
So let's see. Mhm, mhm. Okay. Silver, silver. Okay.
Check the number of bronze and number of
Yes,
silver.
yes, yes. So this is silver, so okay. Okay. Yep, that sounds good. That looks
Everything sounds
good.
good?
Yeah, everything looks good. Yes.
All right, in 2 minutes, we'll start the award ceremony, and let me broadcast this inside of the chat. Let's see. Hope you guys won't be
Yeah.
able to see anything.
I think our team this year with Jeffrey, Luyu, and Z is very, very efficient. We get things done very fast.
Finish the tournament on record time.
Yes, yes, this is record time.
Record time. Cool.
Jim, who's your supervisor?
My supervisor. Well, maybe I will not say it in the stream, but I can tell you by DM. Yes.
Okay.
Yes. Yes. So my supervisor is sort of between physics and chemistry. So he's like cross appointed, and then I'm working on things sort of half on the quantum material side and sort of half on the electrochemistry side. It's a sort of a hybrid sort of project. Yeah. I really want to publish in a physics journal someday. So far, only chemistry journals. So, yes.
Jim, you are in doing a research in chemistry.
Well, our group's lab is in Ash Miller. Yeah.
Ah, I'm a Lash Miller too.
Yeah.
Who is your supervisor? Sorry.
I can send that to you too on DM. Yes. I don't want people to go and search up my supervisor and
I
well,
see.
Jim, I think if I don't know if there's a chance if I look up your names on the Google, I might be able to find the lab to have your
if you know my
your Chinese name, yes.
if you know my legal name, yes.
Yes,
You
I
can
found.
find
No,
my
no, Jim. On U of T website, you have both your Jim and
yes,
your
yes,
legal
yes,
name on
yes.
Oh
there.
no.
Okay, I see you. Thank
Yes,
you.
you can find
This
Okay,
is
thank you.
Stalking on
I
stream.
think I think our supervisors plus I think someone else is probably the only three that are cross appointed between physics and chem.
Yes, yes.
Yes.
But you're a theoretician, right? If I remember.
Pardon?
You are a theoretician, theoretical.
No. I'm experimentalist. Yes.
Ah, okay. I remember that you were in particle physics. I don't know why.
No.
Okay, okay.
I'm a.
But sometimes comes to take donuts on Friday
Oh yes.
on grad
Yes.
lunch. Yes.
Yes. I will try to get a office in MP so I can get that key to go into grad lounge, you know. Yes.
Ah, I see. Anyway, just messaged me and I opened, no worries.
Yes, for sure. Yes.
All right. So I guess we can start the award ceremony at this point. Jim,
Yeah,
are we
we
good
can
to
start the
start?
award ceremony.
Yeah, we're kind of early this year though. On the schedule it says 7:30, but then because we finished the finals earlier, we can start our award ceremony, which I believe most of you guys are interested in seeing who wins the final and and who gets the gold medal. So first of all, I want to thank everyone, like every participant, every jurors, and all the volunteers that participated in this year's CaYPT. Um, there's a objective comment between me and Jim's about this year's CaYPT is that it went really smooth and there was barely any issues comparing to previous years. And we sincerely appreciate all the jurors and also the volunteers for helping us organizing this big event this year. And this year is the 10th year anniversary. It's a very special year, and Jim will later give a closing speech about this. So this is how the award ceremony is gonna go. Another YPT style of presentation. So first of all, we will talk about the individual awards first. The best theory awards, best experiment awards, and the leadership awards. And the theory awards, all these awards are decided by nomination and later on by the committee member checking on the reports and also the score sheets. And eventually we decide who wins this individual awards. So with not much being said, let's move on to the first individual awards that are handed out to someone. So the first award is the Best Theory Award. This award is dedicated and presented to the individuals or the participants who presented extraordinarily well theory and well explanation of the theory towards the jurors. And after several nominations, we have decided that the Best Theory Award goes to Ariel Chen from girls team, which is the team from Hong Kong, China. Is Ariel here, or if is she here in the chat? I know it's 8 a.m. for Hong Kong, and they just went for an overnight flight. I don't know if they might be awake.
No, I believe Ariel is not here right now. We can
He's
move
not
through.
here. Or if anyone is in Team Hong Kong or girls team, please inform Ariel that she won this award
We
and
can
she can now claim
screenshot and
her.
DM her.
Yeah,
Yes.
yeah, we can someone can screenshot DM her. I will send her this virtual individual best theory award. Okay, so let's move on to the next individual awards. We have the Best Experiment Awards. This award is presented to the individual who built a very good experimental device and presented very great calibration as was designs that help minimize any kind of errors within the experiment. And actually, the individual who won this award is one of the individual in the finals. And this person is Alan from Team Operation Ahorn Syrup from Team, or we call it Team Germany. That's what Elaine said. And he's acknowledged for his electrical damping experiment in stage 1. And he was nominated by several jurors. And Alan, do you want to say anything?
I guess I'm very happy. I did not expect to win this award.
All right. Thank you, Alan.
Thank you.
So you may now claim your virtual gold medal by taking a screenshot of this thing, which will say the original image. It will be used at a like a DFT. Okay. So next awards is a little bit special. It's not about science. It's not about any kind of theory wise. It's about the leadership that has been presented throughout this awards, this entire event. So this award is a little bit special. The full name of this award is Mohammed Asadi Lowry Leadership Award, and it comes with a story. So back in 2016, or let's say before that, CaYPT wasn't a thing. We didn't have CaYPT back at this time. Or let's be more serious, is that we didn't even have our IPT team going to participate each year. But it all changes when Mohammed came to Canada. He's from Iran, and he brought in the idea of CaYPT to us, and he formed the first LIPT team representing Team Canada to join the LIPT in, I forgot where, but in 2016. So, but however, it was sadly that a few years later, he passed away in an airplane crash in a really pretty well-known like air accident. And this award is designed and proposed to in memory of Mohammed, and also to acknowledge the individual who have shown great leadership, who are being young while managing the very tough task throughout this entire event. So it's a really special award, and for this year, the company has decided to present this award to the Targo from Team Velocitrons, and they're from the Olympiad School. So is the Tarko here, or is he
He
not
left
in this?
earlier, but me and Justin are still here. So
Sorry?
I'll DM him. I'll DM him.
You're in Team Velocitron, right?
Yeah, yeah.
Okay. Let him know that he got the leadership awards, and it was a great honor and also a very interesting journey throughout this entire CYPT to see the leadership awards being given out to him. Okay. Just let him know. If he's not gonna show up shortly, we can move on to the team's award. It's gonna happen. I guess he's not gonna show up sooner or later. So
Yeah, we can go to the team
let's
awards.
go to the team's awards. Yeah, congratulations. And now let's move on to the participations awards. So the way how the medal works this year for CYPT is that for the top 15% percentile teams, they win the gold medal. And for 15% to 30%, they win the silver medal. And for people 30% to 50%, they win the bronze medal. And afterwards, it will be honorable mention and participation awards given out to the participating teams. And this year is a little bit special because we have international teams. So the domestic medals and the international medals are actually separated into two different regime and calculation. So there will be a gold, a silver, and a bronze for the international regime. And for the domestic team, we have 10 domestic teams. So we will have 2 bronze, 2 silver, and 1 gold medal for this year's domestic teams. So let's start with the participation awards given to the teams. So let's start with Team SMUS2. They're from St. Michael's University, Victoria, British Columbia. They participated in very well in the first day of the CYPT, but for the second day of the CYPT, they withdrew. But we appreciate their participations and their commitments in preparation for this event. And next, we have Team Friction Frogs. They are from Branksome Hall, Toronto, Ontario, which is a private school in Ontario, Toronto. And we appreciate their participations and their commitments throughout this entire event and hope they enjoyed this entire journey. And for the next participation awards, we are giving this to Higgs Bosons. They are from Don Mills Collegiate Institute, Toronto, Ontario. And we sincerely appreciate their commitment and hope they learned a very valuable knowledge throughout this entire journey. And next, we're giving this to Team Velocitrons. And this is a 3 people team. And the team captain is the one who earned the leadership award this year. And we thank them for their commitment and their participation in this event and wish them good luck in the following academic journey. And the last team for the participation awards is Team SMUS1 from St. Michael University School, Victoria, British Columbia. There are a lot of things going on with this team this year, and there are very interesting things that happen, and it's very fun to learn and to know them. And the team captain did show a very, very great commitment throughout this year, and we sincerely appreciate their commitments and participations. So next we move on to the first medal we're giving out. So it's the bronze medal. As we have said earlier, we have 2 bronze medals this year for the domestic team. All the international teams will introduce them separately. And for the first bronze medal we're giving out, it is given to York Mills Collegiate Institute. They are a school in Toronto, Ontario, and their team captain is Yue Kong Wen. And is anyone from York Mills Collegiate Institute here? No one's in the award ceremony. Okay, well, if anyone knows like any members from York Mills Collegiate Institute, let them know that they won a bronze medal in this event, and we appreciate their commitments, their dedications, and also the achievement they have earned, and wish them good luck and in the individual selections and also in the academic journey afterwards. And for the next bronze medal, it is given to Team Physics in Style. They're an independent team from Toronto, and their team captain is Tim Volkov, which we heard that he did a lot of heavy lifting jobs, and also they commit the great responsibility as the team captain. So is anyone from Physics in Style here? Okay, seems like a lot of teams are not in the award ceremony, but we will send them a message and let them know that they won a bronze medal. Okay, I guess starting from now, we are entering the international regime, which is we're giving out the first international bronze, which is given to the international teams in this event. So following the by ranking, so this year's international bronze will be given to Team Sweden. And it's pretty obvious by the name that they are from Sweden. And thank you guys for participating in this year's event. And we appreciate your commitment and congratulations for the bronze medal. Is anyone from Team Sweden here? No one? Okay. What time is it at Sweden and Germany right now? If I remember correctly, it's around like 1 or something.
Midnight. Yeah.
It's midnight, so that's fair. Okay, that's for Team Sweden. And next, we have the International Silver Medal. Before we go into the final, we would like to give out all the international awards before that. So for International Silver, it's earned by Gross Team this year. They are from Hong Kong, China, and they did really well in this year, especially in round 5. They had a really great mark boost, and that boosted them to the silver medals. And we thank them for the commitment and also the achievement they've earned. And I think no one's here because when we announced the Ariel Chun as the best year awards, no one from team group from Grossing is here today. So we'll just let them know and hope they enjoy this achievement they earned and wish them good luck. So I guess now is the exciting part. Now it's the silver medals. So just a reminder that there are going to be 2 silver medals. This is the domestic silver medals. And for the finals, there is 1 international gold medals, 1 domestic gold medals, and 1 silver medals. So let's start with the silver medals this year. For the first silver medals, we have Schrodinger's cats. They're an independent team, but all their students are from University of Toronto schools. I don't know why I say Oakville, but it's from Toronto. And their team captain is Kevin, and they did a very great job for this entire tournament. And congratulations for them for winning the silver medal. Is anyone from Schrodinger's cats here?
Yes.
Oh, Kevin is here. All right, say something.
So hi everyone for Schrodinger's cats. I'm Kevin Lee, the team captain, and my teammates as shown are Pranav, Sasha T, Kevin Wen, and Kushad. I want to thank all the organizers and judges for putting together such a well-run, challenging CaYPT this year. And I want to thank you to all the teams for making every run really intense and fun. We really appreciated thoughtful questions and discussions, and we're really grateful for everything we learned from each other. Thank you.
Thank you, Kevin. Congratulations again. You won the silver medal. That was a great achievement.
Yay.
All right. Now we are going to review the first final participants. This year's final is kind of very stressful because actually the marks between the finalists, they're not that separated from each other. And especially when we're reviewing the marks, we're always seeing some really interesting marking given by the jurors. So we were like, oh, wow, this is interesting finals. And actually, this year's final has a really high quality presentations and everything. And we really appreciate the excellent performance given by all the finalists and all the participants this year. So the first silver medal or the 3rd place of the tournament will be given to Team Excel. They're from Thornhill. They score a final score of 45 marks. Note that the highest mark is 60, so they score really high marks in the finals. And let's congratulate them for this excellent performance. And if anyone from Team Excel would like to give a word, Is Luke Yan here?
Yeah, we got completely washed out. Thank you for inviting us. And yeah, it was a great competition.
Yeah, thank you, Luke Yan. Yeah, but congratulations for you guys too, again, for the silver medals and being a part of the finalists. And we thank you again for the excellent performance today. And good luck with the individual selections, which I think most of you guys will do. And congratulations again. So now we have the gold medals. It's a domestic gold medals, which I think is pretty obvious who will get this domestic gold medals. It's actually Team Shroomskis. They're from there's a 5 people team from University of Toronto schools. They're an independent team anyway. But their final score is 47.8, and they scored really high in front of this finals. And congratulations, Team Shroomskis, for getting the silver medal. Oh, sorry, the gold medal, as well as the second place of this entire tournament. Shroomski, would you like to?
Right, so
Anyone?
Shrimski's actually went for dinner, so
They just went for
they went
dinner.
for barbecue. Yeah.
Nah, we're still here, guys.
Oh, you're still here. Okay, that's first and
All right, all right.
foremost.
Say something, Elaine. Say something.
Yay, thank you so much for all the competitors, all the jurors, and just all Luyu, Jim, and like everyone else, all the admin for making this tournament so unforgettable. We will be back next year, probably.
You guys are all
Maybe we'll
graduating
beat the
next year.
Germans next year. Yay!
All right. Congratulations and thank you, Shrimsky.
Congratulations.
Yes. So
Six,
the last
seven.
and not the least, so we have the international gold medals and also the first place of the tournament, which is Team Operation Ahorn Syrup from Germany. They scored 51.8. They really gapped the domestic teams. And let's congratulate them for being the first place in CaYPT and also for their excellent performance in the finals, as well as the opposition reviews and reports that are really great. So congratulations. With Alan or anyone from Team Germany would like to give a quick talk?
Ja, vielen Dank für die schönen fights. This basically just means in German, thank you for the really nice physics fights we had in general in the 5 pre-rounds, but especially in the finals. There were some really good presentations. It was kind of tricky to find some good criticisms. So I think it was a really high level physics fight that we really enjoyed altogether. And of course, good luck to your individual scoring for the IYPT team.
Yes, thank you. And good luck
This
with
is
your QIPT selection. Maybe we will see the same team in this year's IYPT. And good luck. And thank you guys for participating this year as an international team. It really means a lot for us. And congratulations
Operation
again.
Maple Syrup is a success.
Yeah,
Yes.
it was actually a success. The Canada got conquered already. Canada got conquered before
I
USA
guess this
did.
is better than I heard that Team America was coming to CYPT too. Like they planned to,
Oh,
interesting.
so
they
want to
didn't
turn
show
us.
up in the end. Yeah. So
Interesting.
They tried to turn us to a 15-1 state, but then Germany took the first leap. All right. So lastly, with all the great things that passed by, like it was really quick. It's only 2 weeks, and a lot of great things have happened, and we had probably one of the best CYPT in our history. And because this is a so meaningful CYPT this year, we would like to give a special speech by Jim, the head of the company of CYPT. It's a closing speech, so Jim, I guess you want to take the lead.
Yes, I'll take it away. Yes. So first of all, good evening to all the Canadian participants. Good night, I guess, to all of the European participants. And then good morning to all the participants in Asia if you're watching at a later time. So as you know, I'm Jim. I'm the head of the CYPC organizing committee. And thanks to Jeffrey for the warm welcome. And I'm honored to give this closing speech for CAYPT 2026. So firstly, I want to congratulate all the participants for completing this 2-day competition that spans over a week. You've done some incredible work in your time preparing for the tournament and also did an amazing job during the competition. And I think completing this competition is quite an achievement in and of itself, and you should be really proud of yourself for it. And of course, I would also like to congratulate all the medalists for their outstanding performance in CaYPT. As Jeffrey has mentioned, this year marks the 10th anniversary of the CaYPT, and Canada was first involved in the IYPT since 2016, and we ran our first national tournament in 2017. And this year, as you know, we have decided to take a big step forward and made the decision to invite international teams to join the tournament. And we had this vision, right, of boosting participation, enhancing diversity, and also building friendships across the world. And to this end, I believe our first attempt of bringing international teams to CaYPT is a remarkable success. And we're hoping this experience is a positive one for all. And we appreciate the enthusiasm of all the international students, staying up late at night to compete and to, bring their best work to our competition to discuss with the Canadian students. And I would like to especially thank all of the international team leaders, Nicholas from Germany, Wing Ki from Hong Kong, and Elvera from Sweden for bringing your teams to CaYPT. And a very special thanks to Sam from Sweden, the LOC of IYPT 2025, for helping us sort of spread the word to the international juror recruitment, to all of the jury team from IYPT 2025. We actually, I think, got some jurors from actually not within these participating countries, which it really surprised us in the beginning. But then later on, when Sam explained it to me, I was very grateful for that. And next, we would like to thank all of the jurors for their hard work. Although our student population distribution remains somewhat bimodal across the country, but we do have Canadian jurors coming from across Canada, from coast to coast. And it is the professional insight that you are bringing that provides students with such a unique learning experience and makes CaYPT a truly national level competition. I would like to give a very special word of appreciation to all of the international jurors as well for working through all the difficult time zones to bring your diverse insights into the competition. And also big thanks to all of our 8 chair jurors who are there for all 5 of our selected matches. And they are really the backbones of the competition and helped us resolve many problems using their expertise of judging in the past CaYPTs. And next, I would like to thank all the volunteers for putting in the time to help with the timing and the general organization of the tournament. Although many of them are new to this competition, they very quickly learned how the competition works. And then I think they did an amazing job of ensuring, the clocks are well managed and also the scores are entered in accurately. Finally, I would like to thank my amazing team of committee members, Jeffrey, Luyu, and Z. As all of you have seen, their roles are indispensable. Without them, we couldn't have possibly coordinated a competition of this scale and complexity. I would like to give them credit for all the work that they did. So Jeffrey is the one that helped us with recruiting jurors before the competition. He also, as you saw, ran the opening and closing ceremonies, and he also invited Professor Boris Beverman to give the amazing science talk. And Jeffrey is also our team leader to IYPT 2024 and 2025, and did a truly amazing job of leading and also coaching the team. Luyu, who I consider to be our IT wizard, okay, whenever we need changes made to the system, we essentially just tell him our wishes and he would solve the problems for us. He is mostly responsible for running, maintaining, and also debugging the management system. And it's a very complicated task that requires a lot of dedication. And he is also involved in scheduling and training of the volunteers. And we also have Z, which is the newest member of our committee. She was responsible for the critical work of recruiting, training, and also coordinating all the timing volunteers. This is also a massively complicated task, considering all the last minute changes that we usually encounter. And I think our committee member all did an amazing job solving problems in real time and handling whatever the difficult situation is that the world throws at us. And I think a very interesting and an important point that I want to make is that all of our committee members, including myself, are past CaYPT participants, and all three of them are sort of, to an extent, my students. So I think this speaks volumes about the achievement of the pedagogy of CaYPT and CaYPT program in inspiring and training the next generation of scientists and engineers who are not only exceptional academically, but also very strong in terms of leadership, communication, and collaboration. And last but not least, I would like to thank Ryan Lin, our former IOC member for Canada in the CaYPT, and the school that he is affiliated with for generously lending us all 8 of these Zoom accounts to allow us to host this fully online tournament of this scale. And so all that being said, I would like to declare the 10th Canadian Young Physicist Tournament 2026 closed. And I hope everyone had fun and get some much needed rest. And we hope to see you again next year. Us committee members might stay in the voice channel if you want to have a chat. And this is our informal after party. I would like to say goodbye to everyone. And
Thank you very
Good job,
much,
everyone.
everyone.
Thank you very much. Yeah.
Thank you, Jim.
Sorry, just
Good
one
job.
Thank
last
you for
reminder.
everything, Jim.
Bye.
One last
Thank you.
reminder,
Bye.
guys. For the internet Canadian CaYPT, we will start our individual selection soon. So if you want to learn more about the individual selection and how to get into Team Canada, look it up on the website. It's on the CaYPT website. And this year we'll have a training camp and we'll have an in-person selection in there. So have fun and be prepared for the upcoming CaYPT.
Good job, everyone. Yeah, bye-bye.
Good work, everyone.
Thank you.
Bye.
Thank
Good
you.
luck.
you.
Bye.
Bye-bye.
Good luck to everyone.
Congratulations.
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 Oh, people start showing up in the. Hello, I'm still in the Zoom call.
Yes, we can end the Zoom call and cut the stream. Yes.
Yes. All right. Fantastic.